Here in 12 years, probably, if not more. So it's kind of fun to open the doors. As you can see, I have a very, very mild obsession with tools, right? So,
Do you have one with Rob, though?
no, Rob's got me beat. I'm pretty sure. The only thing, now we do have Iron in the Hat is on the table out here, so if you wanted to contribute something to Iron in the Hat, that's where it's going to happen right there. Probably throw some stuff in there here a little later. I got some other stuff I can throw out there. And then there's a couple of different areas. There's chips and salsa. There's 2 ice chests full of water and Coke over here. There's a table. So eventually, the one thing I'm going to ask is, as we get into this, if you want to visit or hang out and talk, I'd please just request that maybe you go out to one of the tables or step out front, because it's going to be, otherwise it'll be hard to carry on conversations in here when the machines get fired up. All right. What I wanted to do today is to just do some. I'm going to start off with absolutely basic pattern. Well, yes.
Has 2 questions real quick?
Yes, 2 questions.
One, Iron in the Hat, since you're selling it, who's doing the tickets?
Okay,
those
so
kind of things.
First question, let's take them single file. Who's responsible for Iron in the Hat?
They're figuring it out right now.
Okay, they're doing the work on it right now. So they're settling on who's the Iron in the Hat, or how we're going to do the Iron in the Hat right now. I got a bunch of soup cans or something. Maybe we'll just write numbers on a soup, or I don't know. We'll figure something out. What we can do,
Write a bunch of numbers.
or you can just have people write their name on something and put it in the soup can, and then you pull it out and it's just a name.
There you go.
Right. I've got 30 soup cans on the back wall over here if you need them.
That'll work.
And I got scrap paper if you need scrap paper.
Not that I'm a hoarder. And then the second piece of it. Oh, you had another question really quickly.
No, just real quick. Remember to sign in, since they did bring that up. Make sure that you stop in, even if you signed in this morning. Make sure that you sign in. Sorry about that.
Now, in this demonstration, I'm going to be doing a little bit of MIG welding. So, I mean, if you are familiar with welding, please don't stare directly at the bright, shiny light. Otherwise, you can cause permanent and severe ocular damage. Or, if you like that kind of thing, stare directly at the bright, shiny light. And, yeah, it works. Sometimes it's a train. Sometimes it's heaven. So, what we're going to start off with today is I kind of am going to do a really, really fast and loose crash course in pattern welding. Okay? So, I mean, we're going to forge a couple of very small billets, just the process, just to show you the process. These are tiny little billets, right? So these billets, when you're done doing any kind of significant patterning, this is just barely going to be enough for a decent knife. So this is why I use these about as my baby billets. Then we're probably going to do, we are going to do an initial weld on a stack like this, but in order to make this make more sense, what I wanted to do was to actually build a stack right here in front of you and talk through the thought process in where patterns come from, okay? So not only are we going to talk about pattern welding, materials choices, but I also want to talk about like initial patterning. So we're going to be pulling out I've got a whiteboard here. I'm going to try to find a place to prop it up, and we'll walk through material selection, the colors, and just kind of an idea of how we set up a pattern in order to get to some of these wild patterns. And have you all seen my pattern work? Right. Let me hand a couple of billets around so you guys can get a look at them and just kind of. You can just break them up, hand them around, let people go and see them. Now, the idea originally behind pattern welding was that you were going to take a bunch of materials, you were going to stack them together, and forge weld them. This is pattern welding also, not Damascus. Like everybody gets Damascus steel, and pattern welding is used interchangeably, right? But it is not the same thing. So purists will argue that Damascus steel is actually like you're talking about a steel that has a structure inside of it due to the method, or due to the way that it's forged, the actual atomic structure inside of the metal. And in pattern welding, we're dealing with something entirely different. In pattern welding, what we have is we've pre-selected materials that have known metallurgical characteristics, and we're lining them up because of said characteristics. So we're choosing metals that will either etch black or silver or some gradient in between, right? So today we're just going to keep it simple and just talk about black and silver, right? So in doing that, plain carbon steels, just like they sound. So I'm going to feed into my ADD here real quick. I'm going to take one of these little billets and I'm going to throw it in the forge since the forge is running. So while I'm explaining stuff, this one's going to be coming up to heat. We'll take a heat and weld it together, and as we're doing that, I want to build a billet right here in front of you, and then I'll weld that together, and we'll get that sucker thrown in there. And when we get to the big billet, we'll use the Chambersburg to knock it down and reforge it. What we have here, though, as I was saying, we have 2 different types of steel. We have a plain carbon steel. This is 1095, so 1095. In the ASME steel system, numbering system, ASIS. ASTM. I was brain farting for a second. I knew that wasn't right. ASTM steel numbering system, 1095. The 10 indicates it's a plain carbon steel without any alloying elements in it. The 95 is 0.95% carbon. So this is a hardenable American tool steel. Then the other metal that we're using in here is 15N20, and that's a Swiss saw steel. It's sold by Utterholm and a couple of other companies, such as New Jersey Steel Baron makes their own version of 15N20. Now the thing about 15N20 is it's about 0.7% carbon, so it's still a good hardenable steel, but it has a high concentration of nickel in it. So nickel is a shiny metal, for lack of better terms. So nickel, when we go to etch this billet, after it's forged welded together, the 1095 is going to etch out black, the 15N20 will remain shiny or silver in color. So if you ever looked at the knives that were on the table over here, the pattern, the silver portions of the pattern are 15N20. There's a couple of other metals that you can get silver with, like a K600 or 203E, but most of those are low or medium carbon. So you kind of sacrifice hardenability for coloration. And for me, that's not going to do. So for me, I like using steels that are all hardenable and have similar hardening characteristics. So let me throw this in the forge, and I'm going to come back here and talk to you for half a second. Now, traditional pattern welding, the patterns naturally present themselves on the side of a knife, right? So a traditional pattern welding, you just take layers, you smash them together, you keep running the layer count up until you've got 200 or 300 layers, but the layers present themselves on the side of the blade. So all you have to do is just grind a knife out of it or forge a knife out of it, and you're going to have what they call random pattern, raindrop pattern, twist pattern, or ladder pattern. Those are the big four. Those are boring as hell. Right? They're production patterns. This is one of the reasons that you see like a lot of the Pakistan Damascus that's coming out is straight up rainbow, ladder, twist, or a combination thereof, right? I mostly specialize in mosaic, and the delineating line between between these lamellar patterns and mosaic patterns is that I'm not concerned about the side of the bar. I'm looking at the picture I'm drawing on the end of the bar, right? And in order to do this, you have to stop thinking in layers and start thinking kaleidoscopically, right? So you have to start thinking like a kaleidoscope. You're going to make a pattern, then you're going to replicate that pattern however many times you want. Then you're going to reorient that pattern, and then you're going to cut it into pieces and weld it back together to make a circular or some master pattern. This is where this board comes into play, right? For me, he gets mad at me about this all the time because he's like, "How do you see this?" And I'm like, "It just makes sense." But it doesn't work that way for a lot of manufacturers, and I understand that. How are we going to do this? We're going to adapt and overcome.
You need someone to stand up there and hold it?
Oh, look. These things hold the world together when you're a school teacher.
Parents get upset.
I felt like erasers and markers and fancy stuff. So check it, yo. So here's what I was talking about. We're going to start off with an initial stack. And that initial stack is going to have layers of dark material, and then it's going to have layers of light material commingled with it. The orientation of those layers is it's not inconsequential, really. It's actually extremely important. Because if I just do your standard stack where it's light, dark, light, dark, light, dark, light, dark, I'm not painting a picture. Right? It's just light, dark, light, dark, light, dark, light, dark. I want to paint a picture. So in order to think about this, you have to understand where you're going. So let me just kind of walk you through the steps. Typically, you forge this down, and you're going to end up with thin layers of representation of whatever you started with. Then we're going to cut it into 4, 5, 6, 8, 10 pieces, whatever we want. We're going to restack those members, again, to duplicate or replicate that pattern. That gets our layer count up. After that, we're going to take that piece that we forged, and the pattern is going to be running through the piece this direction. If I rotate it 45 degrees and stand it up on the diamond, those layers are moving diagonally through that pattern. I can forge the corners in, and what it's going to do is it's going to bend the pattern around the corners. And it's going to give, all the pattern is going to basically look like it's coming out of a corner of the bar. Are y'all tracking that? And then from there, I can cut it into 4 pieces and restack it in a radial pattern. So now I can basically bend the pattern however I want. So I can have it kind of blowing up out of the corner, or doing whatever kind of kaleidoscopic junk I want. I know this is a crash course, and if you have questions, just ask, blurt them out, right? Questions about this, not about like birds and bees and stuff like that, right? It gets awkward then, because I'm like, in times like this, it's confusing. So, too much, too soon? Okay, check it out. So here's the idea. This one is not welded together, but here you can see the 4 pieces that have a pattern in it, and they're organized together waiting for their final forge weld, right? So I'm going to hand this around, and you can see that there's pattern all in each piece, and all these were originally one bar and were cut apart and welded and were set up for this final weld. As I hand this around, this zip tie, remarkably sharp. Please be careful with it. And just take a look at that. And this is what we're going to be working towards, is just a radial pattern, right? Now,
So the only way I have of flattening material is just on one of these 12-inch discs.
that's great.
Is that good enough for this?
Totally. As long as you can get it flat. I mean, I do it with a grinder. These I'm going to weld up without even touching them with a grinder, because I prison trick number 1, right? Muriatic acid. I hate grinding. I hate grinding mill scale off of stuff. Earlier in the day, somebody asked me how I would get all the mill scale off, like off of that candlestick, because I was complaining about it being all scaly. And she was asking, would you heat it back up and wire brush it? And I was like, no, I'm going to throw it in a bucket of muriatic acid. I mix it 3 parts water to 1 part acid. It just makes a pickle. You can throw your parts in there, and 15-20 minutes of soaking in that, the scale falls right off. So I mean, those pieces are directly out of the muriatic acid. You can see most of the scale is falling off, and that's why they have a little light rust fatigue.
Yeah.
So, did you all see how much flux I put on that billet?
Around 0.
That's right. I give 0 flux. Correct. No flux given. So, we have been lied to our entire young lives. As blacksmiths, we have been lied to. And we've been told that we have to coat everything that we want to stick together with copious amounts of borax, right? Absolutely untrue. Categorically untrue. Not true at all. So I just took that billet, raw as it gets, and I just threw it in the forge. And it's been sitting in there for, I don't know, a while, whatever, right? I'm going to go over there, I'm going to air this hammer up, I'm going to bring it back here, and I'm going to smash that billet. I'm going to squish it down about 25%, which is the industry standard for achieving a quality forge weld, is about 25% reduction in cross-sectional area, if you read the books. And from there, I'm immediately going to turn it on its side and forge it from the side. So all of those layers that were laminar, that were getting welded together, I'm going to stand it up and I'm going to beat the hell out of those layers. And if there's a bad weld in there, what should happen? Right, the whole thing should just fall apart. What do you think is going to happen, though? You're supposed to be supportive, dang it. You're supposed to be like, man, that thing's going to stick. It's going to be perfect. I got these stairs. Oh, yeah, no, that's all I had floating around.
Let me see fast around there. How many times have you screwed that to get to that pattern?
3, that's on its 3rd one. Okay.
The middle's one, and your 2 edges, another one.
Yeah, the middle and then the 2 sides, and then re-squared and reoriented. Now this is its 3rd, going to be its 3rd cycle.
Then how far are you planning on going with that one?
This bar, believe it or not, is not ready. I wish y'all could see this. The bar where it was sitting, or the piece where it was sitting in the forge, the bottom of it is a little cool. Now, I'm judging this entirely by eye, but I found it historically. I'm within probably about 25 degrees usually when I'm looking at it. I was doing a demonstration in Pontiac, Illinois, and somebody was like, I don't believe that is 2,550 degrees. And I was like, whoa, monsieur. I grabbed my thermocouple and stuck it in there, and I was within like 6 degrees. You get used to seeing the color of it. The thing that I'm looking for when I look in the forge is that I'm looking for it to be uniform in color with no dark spots or no unevenness in it. Now, do you all remember what the carbon content I said this steel is? 1070 or 1095, right. Now here's an interesting thing, is if you understand the phase diagram of steel, if you ever look at the top line, it indicates that as carbon content increases, melting temperature decreases, right? And the same thing is true about welding temperature, is that as our carbon content increases, our welding temperature decreases. So I mean, how many of you have struggled with forge welding mild steel? Right. You are setting yourself up for failure from the beginning. Because mild steel has an extremely low carbon content and an unregulated alloy content. So I mean, they are only worried about minimum tensile strengths and yield strengths. They are not worried about if it has a little extra chromium in it here or there. I've hit chunks of mild steel that were as hard as woodpecker lips, and when I put them in the tensile testing machine, they came out at 88,000. What was it? 88,000 pounds on a piece of mild steel. Right. We did tensile tests on mild steel, and it was up in the tool steel category. So because of that uncontrolled alloy content, welding mild steel can be real pain. So if you're just starting off with forge welding, I would strongly recommend, try doing a little forge welding with an old file, farrier's rasp, an old piece of spring steel, not leaf spring. Leaf spring is typically 5160, has a higher chromium content, can be a real bear to weld. But if you can find a plain carbon steel, an honest carbon steel, which is usually, your coil springs from garage doors, flat coil springs from hose reels, files, basic tools like that, those steels would be much, much, much more simple to forge weld. Now what we're doing here is just a simple, back in the day they used to call it a faggot weld, where you just pile material up and smash it, right? And essentially that's what we're going to do here. So if you guys don't mind, there's no flux, not a drop of flux, so there shouldn't be stuff flying around everywhere. But either way, please, if you have it, please put safety glasses on. What's that?
No 40 either, not WD.
No, nothing. Drier than a popcorn fart.
Good.
The only thing I'm using is hate.
Is he?
This is marinated in hate.
Pissed off at me.
So as with any tool steel, you don't want to forge it much below 1600 degrees. You want to stop it. I like to leave a little bit of heat in it. You saw right there, I just went for the initial weld, turned it 90 degrees and beat it into itself. Drier than a popcorn fart, no flux, no nothing, no WD-40, no kerosene, nothing. And then turned it 90 degrees and beat it mercilessly to prove that those welds are stuck. So you can see on the side here, you can actually see the lines down the side of that billet from the layers of the steel in there. This hammer is really weak, by the way. That was the pedal on the ground on this thing. I'm spoiled rotten. Thanks to you. Right.
Yeah, right.
I have
Rob did it.
I have Rob to blame for these two machines.
Rob did
right,
it.
and $17,000 in debt. So why did it work? Why did it work? Why was I able to do that without flux? I mean, flux, we have to have flux. You got to, right? I mean, if flux fits right under there, it goes to the ground, you can lean on it like a crutch. Right. What do you need for a good weld? Heat?
Temperature, cleanliness, and power.
Temperature, cleanliness, and energy. Like, we got to hit it together, right?
Grind them off.
So, my metal's brand spanking new. I use 1095 for one reason, is because I can order it cold rolled. Cold rolled means that it doesn't have mill scale. Mill scale is trash. So if I have dirty metal, I've got to grind every single piece and get it shiny to fit it together to weld it. If I'm buying 1095 cold roll, I literally run it through that little shear over there, going blink, 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 make a pile of it, and then I take my 15 and 20. Look how dirty that is. It's filthy, right? Horrible. No, it's not. It's clean. Again, this metal doesn't, 15 and 20 really doesn't form scale per se. So I can immediately go from cutting to stacking to welding because my surfaces, my faying surfaces that are in contact with each other are clean as a whistle, right? Then I fit them up tightly so that oxygen cannot get in there. But this shouldn't be much of a concern because there's one other thing. What causes scale to form? Oxygen. Right. What does flux do?
Stops oxidation.
Exactly. It creates a shell over the surface of the material that prevents oxygen from making contact with the elevated temperature material underneath, right? The steel that we have that's heated up. So if oxygen can't reach the surface because of the flux, then scale can't form. Right. So, I mean, in a coal forge, there's nothing you can really do to stop that. So you need flux.
Yeah.
But in a propane forge, I'm working in a box, and I'm blowing fire into it. Now, do you know the 3 types of flame that you can get with an oxyacetylene setup? You have what's called reducing, where there's extra fuel and not enough oxygen. You have neutral, where there's a balance between fuel and oxygen. And then you have oxidizing, where we have excess oxygen and not enough fuel. If you look at my forge, have you seen how much dragon's breath is coming out of that thing? It's copious. It's like sinful amounts of dragon's breath. That's on purpose. What I do is I restrict the air intake of my forge. You see the foil up on top? That's a piece of nickel sheet that I put up there. It restricts the air intake on that forge to increase the amount of dragon's breath coming out there to where I'm getting 6 to 8 inches of dragon's breath. So if I have 6 to 8 inches of fire puking out of the front of that forge, what does that tell you about what's going on in that forge?
Blowing everything away.
There's not enough air inside of the forge to support complete combustion. Therefore, we have what's called a reducing atmosphere. And in that reducing atmosphere, since we don't have enough oxygen to support combustion, we don't have enough oxygen to scale the surface of the metal anymore. So by controlling the atmosphere of the forge, I limit or eliminate the formation of scale. And in that, the only time I have to worry about is the time it takes to get from the fire to the hammer. So as long as I'm not like walking around lost, staring at the ceiling, trying to get from point A to point B, there's nothing to worry about. And then beyond that too, have you all ever heard of a pesky thing called decarburization? Where in elevated temperature, the surface of a material loses carbon at a rate of about 1/1000th of an inch per hour. Realistically, since we have such a reducing atmosphere, we have a carbonaceous, carbon-rich atmosphere inside of that thing, and it limits. Not only does it limit scale, but it also limits the amount of decarburization that occurs inside of the forge. So, because of a proper forge setup and temperature, we're able to just run this thing without flux, 0 flux. I'm going to go to that big hammer back there because this thing makes me want to cry a little bit.
So yeah, I have a forging press, and so when I'm forge welding stuff, I just bring it down and just smash it.
Hell yeah!
And
This doesn't have enough power to do that. That big Chambersburg does.
Oh, okay. Because I was wondering if I should be hitting it, or because I just smash it to about half its thickness.
Thomas, I see you. Let me finish answering this question. One of the things that you would have to go against if you were using flux is the potential.
I don't use it.
Right. If flux gets between your layers and you do the entire thing, you run the risk of sealing a pouch of flux in between your layers. So that's why normally if you're using flux, you want to nibble. And when I forge weld with flux back in the day, I would insert the billet all the way through the dies, and I would use the back edge of the die. So when I was pulling, it was squeezing all that flux and blowing it out the other end, so I wasn't getting blasted by it.
Right.
But if you go for fluxless, there's nothing between the layers.
Right.
Smash it all at once. Heck yes.
Yeah.
Take it down. Hit the whole thing. Doesn't matter.
Okay. Yeah, I was just wondering if I.
Now, Mr. Powers, your question?
I came into blacksmithing from being apprenticed to a professional sword maker. And one of the things that was pointed out is everyone says, oh, I want to make an enormous forge because I want to make swords. You only want to heat as much as you can work in one go, which is usually like 6 inches, unless you have power damage. And that's what the Vikings used, and we can tell because they did a lot of twisting, and they were using real wrought iron, and you have to work it extremely hot. So if you can look at like the Osler tripod, you can see how much they got hot to do a twist in stages. So, and if you have your forge too big, you have decarburization, grain growth, and scale losses. So you're actually damaging your sword metal.
almost went to autopilot and threw it in the over there in the vermiculite to cool. You can see how much harder that hammer hits. That hammer hits hard, way harder, right? So what I did here again now is I've knocked it down, and this is the beginning of what, it's a W pattern. There's a lot of people that call it crushed W's. It's like, if it wasn't crushed, how would it be a W? It's just a W pattern, right? And I'm going to illustrate this here in a second and show you what this is, because the W pattern is the foundation for almost all mosaic in one way or another. Okay? So now I got a bar. It's drawn to a specific width. Now in my brain, I normally aim for about the same width as my metal here, so I'm a little narrow, because I like being able to use these bars as components in a bigger billet. So normally I'm going to aim for about 1.5 inches here. I'm at about 1.25 inches, which is fine, because I've got some 1.25 inch stock over there that I can make a different billet out of. But this now, what I'm going to do, I've got it forged relatively straight. Got a little hog leg in there. Relatively straight, relatively uniform in width. I'm going to heat it back up again and get it above the 1600 degrees so that it's in it's above the phase change, if you will, the curing temperature of 1333 degrees. And in doing that, I can put it in the vermiculite and allow it to cool slowly, and it's going to become soft, right? So we're going to do just a real crude annealing, which is to soften the metal. And that'll make it to where the material is soft enough that I can cut it with a saw. I could drill a hole with it if I need, or drill a hole in it if I needed to. But for me, what I'm more concerned about is being able to cut it into segments, because I'm going to end up restacking this again. Because remember, these are components, these are parts in a bigger pattern. Cool. I have my Holly Hobby eraser. Here's what happened. We had a bar. We had layers in it. We welded that bar together, right, as soon as it was welded. And remember, I'm usually looking for about 25% reduction across sectional area. So to keep it easy, if that bar was 1 inch tall, I want to forge it to 3/4 of an inch before I consider it to be stuck. I've literally done it to where I've given it one hit with a hammer and turned it on its side and had a successful weld. So I'm not saying that 25 is absolutely necessary. I'm saying that's the industrial standard, is 25% reduction across sectional area. So once I had those layers, these layers are still lamellar here. They're this direction. I turned it 90 degrees, and I took that bar and forged it down with those layers upright. Now when you forge material wants to bulge on the sides, right? So what happens is, if you imagine an imaginary center line, the material bows more and more and more as it gets out to the side. And it bows away from that imaginary center line. So now those layers, instead of being straight, those layers have pooched out. And we have the foundation of what's called a W pattern. All right? And from here, you can square the sides up a little bit so you get less loss. Cut it into 4 or 5 pieces and restack it to get yourself enough mass for another forge weld. And in doing that now, we have this pattern, this repeating W pattern, that's getting more and more dramatic as we go now. So we have a replication of that pattern, right? So here's where I'm going to go to a big billet. What am I going to do now?
Let's heat it up.
Let's put a big billet in and start working towards this. I want to talk. We're gonna do this Quentin Tarantino style. I'm gonna rewind it here a little bit, and I want to start now that we understand this W. I want to take it to a different place before we get going. Okay. Have you figured out that my power hammers are like my drum set? I'm all ticka 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 ticka. The little one in the corner is the cymbal. Chambersburg's the bass. Right? This is like the snare. You know? Gotta have them all, right? Can't just have one. It's a collection. Okay, so what you see in front of you here are different types of steel. What I have is cold rolled 1095 in 3/32 thickness by 1.5 inch width. Cold rolled 1095 in 3/16 thickness. Okay, so the two I just showed you are the same material. 1095 plain carbon steel. What color is it going to be? Boom. You just won yourself a beer later. I don't even know if you like beer, but and if you don't like beer, I just won your beer. Then this is Utter Home. It's called Utter Home Strip Saw Steel. This one actually is laser engraved, so you can actually see that it says Utter Home Strip Saw Steel. And this is sold in a coil, big giant roll. A gentleman named Steve Swarzer, he's a master bladesmith out of Florida, buys these rolls at like 1,100, 1,200 pound rolls, and I call him up and he just shears it to length. So this does not have a sheared edge on these sides. They're nice and smooth. It's sheared this direction. So it doesn't have a rag or a burr or a saw edge or anything. Why do you mention this, Pep? Well, what are we trying to keep out from between the layers? Air, right. So if I have a sheared edge on my piece and I fit it up and that sheared edge is propping the metal up like this, I'm not going to have an airtight fit up and I'm going to have to grind that edge. And grinding takes time, takes abrasives, and it removes material. These are three things I don't want. I want to get done, man. This is cutting into my drinking time. Right? Seriously. So maybe, I don't know, maybe that was a joke. Not with everybody here.
Count his fingers.
People frown on that.
Count his fingers.
15 and 20 saw steel. What color is this going to be?
Right.
Bright. This is going to be shiny, silver color. So we got a lot of dark metal, a lot of shiny metal. That's the shiny metal.
But that's L6?
No, L6 would be the American equivalent of this. This is 15 and 20. L6 is the American saw steel version of that. Oh yeah, thank you. Cruel joke. Barely a wisp. Right. So this is how I typically do this. You'll notice I have 2 blocks on the table. These blocks are there to hold up my material as I start stacking. Now, for this particular pattern, we went light, dark, light, dark, light, dark, light, dark, light, dark. Now what's going to happen? Did I throw another billet in? No, billet in. I'm going to throw another billet in just for the fun of it. Not that I need to weld it, I just have a bunch of billets, so I'm going to throw one in. And while that's heating, right, fire's lit, might as well be making metal. So look at this W pattern. Once we weld it, if I do the turn it 45 degrees, so the pattern is running diagonally, and I reforge it into a new square. So I knock the corners in. That pattern is going to look like it's popping out of the corner of the billet, right? But then at this point, I can cut 4 pieces like we did in the earlier drawing, and I can make a kaleidoscopic version of it, to where I can have 4 pieces with the pattern blossoming out of the corner. Okay? I'm going to pass around a fundamentally, or a much more rudimentary version of this so that you can kind of see it.
I shared a shop with
So this one as I pass it around, what you're going to see is, if you in your mind split this thing into 4 pieces, you're going to see it's 4 of the exact same pattern, okay? But what you're going to notice is that there's a lot of dark material around the outside of that pattern. So the pattern appears to be floating in a sea of dark material. That all starts at the initial stack, okay? So look, with this initial stack, everything is uniform throughout the pattern. With what we're going to do here, what we want to do is we're going to start our initial stack. It's going to be real wide.
Thank you.
It's going to be 4 inches.
That's very kind.
Because that's the biggest billet I can fit in my fork. 4 inches away. Right?
Oh, I'm sorry, man.
I'm going to put heavy layers of black on one side and a moderate layer of black on the other side. And then in the center, I'm going to do alternating silver and black layers, and then maybe a heavy black band in the middle or whatever. But basically, it's going to be an asymmetrical stack. So I'll have 3 big bands of black and then a couple of sections of silver in there. You see what I'm saying? So with the sides being heavy, when I duplicate this pattern out, once it's forged out 3 or 4 times, it's going to have that same pattern, heavy black on the sides, striga black in the middle, and then black on the other edge. So then, when I go and re-square this, you have to kind of imagine that we're going to be making 4 new corners there. So what happens is, when we re-square this, we're going to end up with a black that bows around the corner on both sides, and then those waves are going to be trapped in the middle here. You see what I'm saying? So now when I make a kaleidoscope of it, this is where you start getting the heavy black borders, shocks of black mixed into the pattern, and a black pattern in the center of the pattern. It's just by the way that we stack it. So let's take a look at this. Let me show you in progress, and I also want to show you how. Oh, that's pretty.
So when you forge that out, that end is going to be the side of the knife.
We get into a whole different problem there.
Oh, okay.
Right, because the pattern is presented at the end of the bar.
That's what I was wondering.
That's when you get into the accordion cut.
Oh, okay.
I'll get there.
All right.
So look, check it out. Heavy black band on one side. Oh, that looks good. Then I want to do silver, black, silver, black. Come on. I normally do this on my big welding table instead of sitting out here in the middle of the shop. Heavy silver, medium black, silver, black. Oh, silver. Now, do y'all see what I'm doing? I know I'm going to hold it up for y'all to see. I put the heavy black in the middle. I stuck the silver out one side, and I've stuck the moderate size black out the back. It'll help me visualize the pattern, and then if I mess something up, it's easier to separate them all out again. Right? Not saying that I ever mess anything up, but I mess stuff up all the time. Moderate black. Got a little bit extra silver left over. I'm just going to find a place to shove it into the pattern. I've got heavy. I got a gap here. I can slip one in here. Heavy. Another one there. That's pretty good. I can throw these back in the box. So look. Let me put a clamp on this real quick and I'll show you all.
Pass that back up to the front.
Beth, can I be obnoxious and convince a little more?
Can you be what?
Obnoxious and convince a little more. We had a trade item at Sofa one year, which was a pizza cutter. And actually I wanted to do a pattern welded pizza cutter. So I had a billet of bandsaw blade and pallet
You might want to film that. That's kind of cool, man. Look at the center.
Took lengthwise and forged it down and
That's
put
that
in
round.
without failure of any of the welds. So when some people tell you that, you know, the welds are weaknesses, not necessarily so.
That one, they came back up to the front. You want me to hold it?
Heavy material, silver, black. So it helps me visualize, because I can see where the heavier, like here I put two silvers next to each other, you know, so it helps me kind of visualize, and this is all black. So you can see the distribution of the material in the pattern. But you can see the heavy borders, how they're going to pop up in there. You see that? Cool. Yes, sir.
Is there oil that comes on that has to be cleaned off?
I don't touch it.
Don't touch it.
I don't even look at it. I probably should. I should probably feel guilty about what I'm doing. Like, it's probably against the Geneva Convention or something.
They usually coat all that coal.
The P&O.
Fluorinated oils.
Right. And I've never had a problem with it, though.
Okay.
I honestly have never had. I don't know if it burns off at a lower temperature. And I mean, I've never had it being like really wet, like oily. This is from this clamp. I use it on my power hammer, so that's just junk off the power hammer. Let me get a paper towel from behind here. You had a question?
Yeah, do you believe in silver and black? Just curious.
I've always had a kind of a three-dimensional mind. So it's not that I dream in silver and black, it's that I can just see, it just makes sense. The way the metal's going to move and topple and push and fold and especially once, there are 35 things that you do in forging Damascus that you would never do on a conventional piece of metal. Like on a conventional piece of metal, you would never re-square on the diamond. You know, you never go, I'm going to take this square piece of material and turn it into a square piece of material this way. Because why? There's no reason. But the fact of the matter is in pattern welding, I'm not worried about the external shape. I'm worried about what the lines inside of the metal are doing. I'm worried about the flow of the material inside of that piece of metal, right? So it's a little bit of a different thought process. We're looking at the way that, I mean, this is when you look at industrial blacksmithing books, there's a thing called barreling. When you forge a piece of metal, it tends to move as an X inside of the metal. Because the way that the forces get applied, the metal pushes in, it has some planes, and then the center gets pushed out if your hammer's big enough. I use that all the time, and I'm going to show you right now. How many people here have wrestled with rhombus when you're forging? Like you're forging and it gets knocked over sideways a little bit? That's death to a Damascus pattern, to some of my patterns. Because if I have a pattern that knocks over and my layers are this direction, I can't just drive the corners in because that'll wrap the pattern around that corner. And you end up with this pattern that has folds where the pattern has curled around the edges. And in mosaic, I mean, you can do some pretty cool stuff with that, but it looks like you lost control of your pattern if you know what you're looking at. So for me, if I have a big enough hammer, I can stomp on that thing hard enough that instead of it falling over rhombus and staying parallel, the sides pooch out. Because I can hit it hard enough that the sides squirt out. Then if I need to correct that rhombus, instead of hitting on a point and driving it in, I'm hitting on that curved surface that I hammered out. Let me illustrate that so I can make it make sense. Actually, I will illustrate that in a second. Let me get some of this other stuff flowing so that we're not sat here. Because we're going to have an intermission here in a second. When this big billet goes in, it's going to take 30 minutes to heat up. Okay? We'll take a second, go get some snacks, tea, water, make a bathroom break, and then we'll come back in and forge weld this monster. Cool. I'm going to need this thing for a moment. In a moment. Look at this high quality design. It's only $50, right?
Store-bought piece, man.
They had it marked at the wrong price, and I went and made them honor the price on the thing, so I got it for $30. So I wasn't. Right. I'm just gonna set that right here. Okay. I think I need another extension. back to y'all. That's usually the extent of my hand forging.
Well, use the hammer.
I'm so tired right there, right? Observation, and this dovetails into the concept I was going to talk about when I was talking about scooching the sides out. Did you notice how this hammer the material didn't get wider? It just got shorter? It's because it didn't have enough energy to push the sides out. The bar itself was acting like its own anvil. It's backing itself up. So it was just getting squished and barely pooching out on the sides, but growing in length quite a bit as it nibbled, as the hammer was nibbling at it. When I go to that big hammer, did you notice how quick it just went whop and spread out? Because it can hit hard enough to get the metal to splat out, right? And in doing that, I can gain that width that I need. Because you'll remember I was trying originally to get it to about here. So I mean, I'm damn near exactly the same as the other one, just an inch and a quarter. So in one heat, I went from initial weld, 90-degree turn, started the W pattern and drew it out, and this is ready to be cut and restacked at this point. This is where with pattern welding, when people say, well, you don't need a power hammer, I'm like, ha ha! Wrong! I mean, you can do it in the traditional sense with like fullers and strikers, and you can work tiny little billets. Right, but you're going to hurt yourself. You're going to break yourself down. Pattern welding, like complex pattern welding, is about metal movement. And it's about metal movement for the sake of metal movement. And that's the weird thing. Like, no other place in blacksmithing are you going to take a square, stretch it out, and then forge weld it back into another square. You don't. It's just a wasteful thing. It's an absolutely wasteful process. Speaking of which, in pattern welding, you're going to be faced with a significant amount of material loss due to cutting, grinding, cleanup, restacking, welding, and pattern development. Even the most fundamentally simple patterns, you'll have about 20% loss. And some of the bigger patterns, the reason I start off with a 10-pound billet is if I'm lucky, I'll end up with about 6 pounds. And I have about 40% loss. And that's just in cutting the distorted ends off, cleaning the surfaces, and repeating that process again and again and again. Some of these patterns I have 5 or 7 welding cycles in, where forge it out, cut it, chop it all up, restack it, forge it out, cut it, chop it all up, restack it a different way, forge it out. Then after 5 or 6 or 7 welding cycles, that's 5 or 6 or 7 end cuts. That's 5 or 6 or 7 heel cuts. By the time it's all said and done, these little heels and ends and toes and bits and pieces, they add up. That's lost metal. That's trash. It's not trash.
That's good. That's
You just do different things with it. I started forging tiny little kiridashis or making necklaces or earrings, like surface grinding a paper thin. Stuff like that.
I like wedges for hammers.
Wedges for hammers, right? Hoof picks. I used to make hoof picks for farriers. I'd cut a little larger pieces, or I'd clean them up. Y'all found I told you about muriatic acid, right? So I mean, a lot of the time, some of these more wild patterns, you start off with your pattern standing straight up, and when you forge it, the pattern bends down, right? So you have a huge amount of detail very close to the surface. If you get in there with a grinder and start grinding the mill scale off, you're grinding through that fine detail back into the boring center section. So a lot of the time, if you're doing a lot of heavy grinding on pattern weld, you're losing your surface pattern. A lot of it. Like a lot of it. So you soak it in muriatic acid, mill scale falls off. We don't need to grind. Literally. You can go straight out of the acid, stack it.
You're just going to stack that stuff up, hit it with muriatic, and then be able to re-weld it. You won't.
I will measure it into uniform lengths chunks. There's 2 ways to do that. Here, let me show you. Let me make your brain explode a little bit. So you can use a divider. I put this up here the other day when I was cleaning up, and I never got it back down again, and now I've got to do something really hokey. Haha! Thank you.
Remember I said it wasn't an
Right.
I don't know. The rest of us were sitting here with mitts. Do we keep it if we catch it?
Yes, exactly. It's like the claw game. So if you need to measure it out into uniform pieces to cut it, you can take this tool, you know, and measure out however many uniform pieces you need. You see what I'm saying? So you can walk it across the thing until you know you've got 4 segments, like 1, 2, 3, 4. Adjust your lengths until it's exactly right, and then use this as a scribe to scratch your lines on it, right? Or
you can stop thinking and just figure
right.
everything out.
Oh, that's neat.
if I want 4 segments, 1, 2, 3, and then so I line this one up at one end and this one up at the other end, and then put a tick mark there and there and there.
Wow, that's
If I want whatever the length is, it's a button spacer. If you're looking for them, it's a button spacer for spacing buttons on a shirt. There you go, right there you are.
What's that?
Knobs lock in place, and you can get, this is great for uniform length and pickets. This is great for sectioning stuff off. There's absolutely nothing on this that you couldn't forge or cut, because they're just equal length bars, and the one on the end is half length to the pivot. So I mean, you can make a spacer like this regularly easy. This one is just called point-to-point equidistant measure marker. Got it on Amazon. I think it was like 30 bucks. I keep it in the box because I have the box still. There's a hot tip for you. It's really nice for just, I mean, laying out anything that has to be equidistant. Even if you're just making punch marks that you want equidistant. And so instead of having to measure out, tape measure, and tick, and whatever, this thing you tick, 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 on to the next task.
Pardon, let me put this back in the fire.
You're not gonna put it back up for me? I have a milk crate that usually sits there, and that's why I was able to get to it easy. But I cleaned. My idea of cleaning up for the demo was to move the milk crate. Right. So let's weld a bigger billet. Actually, let me tack this together, and then we'll go from there.
Do not look at laser with remaining eye.
Doctor.
More things for that Roman thing. We're gonna have to have this thing that measuring one. That would be good.
Did my dry erase board go away? I was just gonna set it up here, but y'all are smart enough not to stare at the bright shiny light, right?
Oh, that's cool.
What's up? Watermelons, yeah, I guess. You got it there?
Secret things are happening back here.
Ignore the man behind the curtain.
Man, I was holding the metal behind me. And shiny came right through the thing and burned my eyes. I threw it then. It happens. Don't think about it but once. Don't do it again.
Yeah, yeah. What did it add up to since you just measured it? What was the width on it or whatever?
Just shy of 4 inches. That's usually my target number because it'll fit the forge. But let me show you what I did wrong. Let me be the first person to out myself. I'm working over here, kind of hauling butt, clamping on it. See how it's not perfectly square? I'm already starting off with a little bit of a rhombus. So when I go into forge weld this, I'm going to kind of pat on it and correct it, like literally in the first 2 blows. I'm going to correct that little tiny bit of rhombus and get it out of there. But we got a long way to go because this will get forged down to about the largest. Well, we'll get there. Now, a couple of notes. You see how I put the weld at the extreme corners, front and the back, and then I put a weld straight down the center of the billet. The one in the center of the billet is not necessary. What it does is as this billet is heating, it keeps it from opening up as the billet heats unevenly. Realistically, a lot of people will just weld like a little inch-long tack weld at the top and the bottom, and that usually handles it. I'm not worried about it though, because I'm going to cut this thing up, right? Oh wait, let me illustrate something first. Every metal is a color, right? 1095 is black, 15N20 is silver, so every metal is a color. What color is MIG wire?
Black. Disposable silver.
We don't want it. MIG wire is poison. MIG wire is low carbon. It's not hardenable. It's a little chip of poop in our big bucket of ice cream. It wrecks the whole thing, right? So we don't want that MIG wire to end up in our finished pattern. We're going to have a simple, soft, gray spot right in the middle of our beautiful, beautiful, beautiful pattern that we've worked so hard for. So how do we keep it from getting into our pattern? A, don't use it. B, use it very judiciously. And let me tell you what I mean by judicious use. I put it all the way here at the end, and I put it all the way back here at the end. What's the first piece that we cut off when we developed that pattern?
The end.
Right. So very first thing, when I get in here, after it's welded together, you've got the nose of that pattern, that tongue that's sticking out after it's forged. I'm going to cut that thing off, right? Well, that MIG weld is right here and right there. It's gone. Get thrown away. Now you're asking, whoa, what about the one in the middle? Oh, what about the one in the middle? I cut everything I make into 4 pieces. And I do that for a reason. Because I'm going to have 1 up here, 2 down here, 3, 4. There's going to be a cut right there in the middle. So when I go to restack this, that is either going to be the front of the billet or the back of the billet, that little bead of MIG weld. It's going to naturally migrate into the trash zones at the front or the back of the billet. So after that second welding cycle, when I cut that nose off the billet again, all that MIG weld's gone. There's no MIG weld in there anywhere. None to be seen. Right? So that's why I keep it centered, is because in cutting it into 4 pieces for that second stack, it's going to get moved into the trash zone that's going to get cut off into that waste area that we were talking about, that 20% waste area. Now this works either in the cut and stack method, or also, I mean, if you're just drawing your billet out and cutting it in half and folding it, that works also. Because, I mean, if you're just doing a layer count billet, if I forge this thing out, hack it in half and fold it, the metal at this end is going to come and get collected down here by the stick. And then I have that little bit, if I cut right in the middle, that weld actually acts like my indicator of where I want to cut. Because no matter how that bar stretches, that's still the center of the billet. So that's where I'm going to drive my hack down into the bar to make my fold. By the second fold, that material at the end that used to be the middle, so when I fold it, what used to be the middle is now the front of the bar. Second time I fold it, what used to be the middle that is now the end of the bar gets folded back again. So all of the trash migrates towards the handle. So after 2 welds, all of that MIG weld is back here by the stick and it gets thrown in the trash when you chop off that part. But you've got to put your MIG weld in an area or region in which it will not become part of your pattern. If you are working in an area where there's an outside chance that some of that metal might become part of your pattern, that's when you're better off fusion welding it with TIG. Because if you use TIG and fusion weld it, you're not adding any dissimilar metal. You're melting what's there. And it's such a shallow weld that after scaling and forging and whatnot, more often than not, by the time you've even ground the mill scale off, you've gone through the distortion caused by fusion welding it with TIG. Cool. So
yeah, I always put 1/4 inch plate on top and the bottom of the billet just to keep things from wrinkling, but apparently you don't think it's necessary.
You don't have to, but did you notice how I stacked this thing?
Yeah.
You notice how the heavy material's on the outside?
Yeah.
I did that inherent. Like that wasn't, Anytime I have the option, I'm going to put a heavier, thicker layer on the outside so you don't get the distortion or wrinkling on those outer layers. I'm also, if ever given the opportunity, I'm always going to try to put a plain carbon steel on the outside. So like put a 15N20 or 1095 on the outside, just because it's way easier to weld in general than it is if you have like N20 on the outside where it can form weird oxides or it's just in general it's easier to weld. It's that plain carbon steel, especially on the restacks.
Okay.
Let me throw this monster in here. Let it start heating up. Oh, real quick. Scale sucks, right? So this is one of the things that hydraulic forging presses are horrible about. With a forging press or a rolling mill, the scale on the surface of the billet is going to get driven into the surface of the billet. And you're going to end up with scale like rammed down in there, like a 1/16 of an inch or more a lot. In my very last heat, I almost always come in and gently pat the billet from the sides, so on the narrow cross section, and the scale will flake off. And then I can do a finish pass, and it's scale free at that point. I'm going to do that so that you can see it here. So I'm going to come in and just pat, 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 pat. You'll watch the scale flake off. I'll do a finish pass, and then this other billet's going to go in the hammer over here. And I'm only doing this because this thing's been sitting in the forge for like way too long. So watch the scale. Look how clean that surface is now.
Yeah.
So you let the hammer do the work, man.
So that's flat enough to stack.
Oh, hell yeah, man.
Huh?
That's
Okay.
flat. That's flat.
Huh?
Muy caliente. Doesn't take me long to check out a billet. That's what.
Get better.
Look at that.
Yeah, it's straight as an arrow.
Still calibrated.
The dies are flat.
Yeah.
Let the dies do their work, you know. The problems come in when you try to forge like this or like this. So I mean, if you see your stick, like when you see people holding their tongs and moving a billet like this, they have no idea. There's an axis, there's a plane under this machine that if you are on plane, that stick should remain dead flat, and that bar should just move. There should be no bucking, no twisting, no thrashing, and it shouldn't be inducing a wave or anything into the part. On top of the barrel because I can't tell you how many times I've been out here working and I make like a bunch of billets, and then like a month later I go and open the lid and there's like 7 billets in there that I forgot about because I was just like on to the next great thing, you know. So I leave the tongs on top of the bucket because they're out of place and my brain sees them.
When you get over, you're going to do a couple of things at a time, and that's it, bud.
Right?
Yeah.
Right. And one of those is going to be breathing. And then
Only
work.
if you're lucky.
Okay. I made these tongs out of sucker rod specifically for this. I like having an end on them because it tells me where the back end of the tongs is. They're kind of based off of Farrier pattern, and they're just made for 3/4 inch sucker rod, which is what I make my sticks out of. It gives me a lot of good control. You'll see people, let me throw this in the forge and I'll explain why. You'll see people weld a big long bar onto their Damascus. You ever seen this before? Big long handle.
I always just weld a piece of rebar.
Right. And then when you're working your front hand, do you ever just destroy your front hand, burn your gloves? And the stick gets hot and gets all wanky and out of control?
Yeah.
Right. That's the problem with the big long handle. I mean, I used to use big old, like, yes. It's like jousting, you know? But I used to use these big long bars, and I'd weld the billet to it, and I have this big stand that comes out, you know, to hold this thing, and I had a heat shield to fit over here to try to keep the handle cool, you know, but you found yourself working billets like this, because these big billets are in there for 30 minutes, you know? This bar is smoldering hot up to here.
Yeah.
So the stub and a good fitting pair of tongs has really changed that process. And if you're working the metal at proper temperature, the metal is so soft that there's really no shock through the handle. If you're getting any feedback or shock through the handle, you're working your metal too damn cold. And that's where it gets dangerous with a power hammer.
Right.
Because if the handle is cool, or I'm sorry, if the stick is hot, if you get an errant blow, if you're a below center or above center, it's just going to bend the bar. But as things start cooling off, if you're above center or below center, it's going to knock the tongs out of your hand or flip them up into your face. And that's where it gets dangerous, you know? So working at the appropriate temperatures, especially under larger hammers, is kind of important. Speaking of larger hammers, we're going to be running the Chambersburg for this next weld. So I'm going to prep it. And and then I'm going to kind of retreat a little bit and open up this space for you all so that whoever wants to kind of pile in, you're welcome to get behind the forges here or in this area over here so that you can have a view of that hammer. It's going to go fast. These billets, like what you saw me doing with those little itty bitty billets, that hammer does with the big billets.
Oh, you going on chamber?
Oh yeah, we're gonna run the chamber. I love that thing, but one of the things about that hammer is that it takes over the shop. So when you turn that hammer on, this hammer, even though it is a giant blue turd, it's quiet, right? That little giant, it's got that soothing hum of that flywheel moving, right? So it's quiet, and when you need it, that thing gets rowdy. The Chambersburg, when that thing is on, it owns your shop. You're not having a conversation. You know, I mean, everything is high fives and yelling at that point. You know, smiles from ear to ear for me too. But that hammer it's a self-contained hammer, so it's extremely loud. This particular hammer is a 1948 Chambersburg. It was delivered to Kaiser Steel in Utah in September of 1948, which is one of the reasons, the only reasons that it's still around. Realistically, most of these 200-pound Chambersburgs were built under Navy contract to go on Navy vessels. And at the end of World War II, the Navy had options. I can bring home 8,000 pounds of hammer, or I can bring in 8,000 pounds of soldier. So where do you think the hammers went? Right off the side with all of the P-51 Mustangs, with all of the Corsairs. They pushed them right overboard. Conservatively, I've found somewhere in the neighborhood that I know of about 25 or 30 of them in existence still. They're rare birds. Not as rare as the 300, but they're rare birds. They're renowned for being an insanely hard-hitting hammer, but not having a whole lot of control. Like a Nazel is like a Cadillac hammer. It's ultra fine control and good power. Chambersburgs are just like all power. And they're fun. And this one has decent control. It really does. But it's a blast. It's a beast. Yeah, so we're gonna run it. It has a 10 horsepower three-phase motor. So in order to run that thing, and I'm gonna let it warm up for a minute. So this is kind of where we're gonna take intermission, and that thing's gonna take over the shop. And I'll holler at you all when we're getting ready to run it. But I turn on the face converter over here that takes my three-phase power. Comes down in a hurry.
that's how much can fit in one of those forges with the whisper burner or whatever. So the problem is we don't have a hammer big enough to work a billet that big most of the time. You got plans to get something that big?
If I win the lottery, I'll have done it for me.
Like that.
Cool, man. So there's a little chunk of Damascus for you.
Still calibrated.
A little bit. I didn't even check the width. I probably should have checked the width before I sealed up.
Why are you so tired? You want to sleep?
I'm not tired. I got another 6 hours in the easy. I'm just changing gears. I get tired of listening to the hammer. I really do. After a while, you know, and it's music in my ears, but after a while you're just like, you know, if you're not going to use it, might as well turn it off.
Sounds like a good problem to have. I mean,
Right?
What is that thing getting going on the shit?
Could you imagine that?
Yeah, you're like,
Sitting on a steel plate down inside the machine shop, the machine room.
you already got that on 4x4 or
Imagine that sitting on a ship. Jesus. Bounce the ship over there.
Pretty damn close. The nice thing about a big hammer is it makes it a little easier too.
If you're gonna throw it away, throw it in the back of my truck.
Yeah, I'm within a 30-second of an inch. I got a skinny spot right there that's out of 30-second of an inch. But that'll stack. The reason that it's important to get a good uniform width and thickness. Thickness isn't so critical as width. If your width is off, the overhang can really mess you up. Because that's material that's unsupported, kind of hanging out there. So you want, I mean, if you can get your width the same, that makes your stack so much better to keep your stacks like this here, you know, where they line up. So you don't have material that's going to have to be ground off or have overhangs. Because then it makes it much
Closer. That one, they're both great. It's a little bit off.
You think a 30-second is enough to
So-
mess you up? Oh, okay, that's what I was wondering. I'm like, dang,
What's the number that throws you out?
Really depends on what you're doing next to this step. But here's the bigger thing. It's like, watch. I'll show you this. See all this material here? See how there's a step here? From here down, that material was lost. So if you think about it, if I come in here and draw a line down the side of this thing, all that material outside of that line is lost because it's only as effective as the skinniest piece. So when I forge weld this, that material is going to bulge out, and it's going to be lost. So if I had to do this billet, if I had to attach a stick to it to weld it, I'd weld the stick here. Because I'm going to be chopping. Eventually, this is going to get cut off anyway. Now, here, let me tell you a bigger issue. Is sometimes it's actually better to grind it all flush from the get-go. Because what will happen is that this bar will actually get driven down into the bar underneath it, and because of the extra material, it will actually bend the pattern as it gets pushed in. So you'll get a significant amount of pattern distortion. I learned this when I used to do 4 bars like this. I thought I was being crafty because I'd leave it attached to the stick, and I would just cut 3 pieces off, and I'd have the stick still welded onto the one original piece. So one of these members would stick out further. But then when I forge welded it, all of the patterns would slope in at the end because that extra material back here made the pattern move at an uneven rate. So I found overall it's better to square everything off and just start with a flush back and weld on, because, and let me tell you what, that distortion would move into the material a little bit, so I'd lose a tiny bit more material because of that pattern distortion from uneven cutting, right? But bigger than that, if I just square everything up and then weld it and cut it off nice and clean, once you're done welding it, that piece that you cut off is absolutely pristine. So it's not lost material. That pristine material, then you have this little absolutely perfect tile that is a record of your pattern. Or you can make a necklace or jewelry or whatever out of it. Y'all haven't seen my scrap bin, have you? Hold on one second.
He's like, let me go grab all the earrings.
You don't like him, so he's going to give everybody one piece.
This is all one pattern. This is the development of just one pattern. That's why it's in a separate bag.
But it gives you like a memory, like, oh, I remember that.
Well, on their roadmap, the pattern is the record of it, you know, so.
Can you look at a pattern and know how?
Most patterns, I can look at them and just kind of. You identify party lines. Typically, when I get to this point, if they're not this square, see how square it is? If it's this square, I don't usually cross weld it. Because when they're square like this, if I hit it with the dies, it comes together. It's when they're rhombus at all, there's always one plane when I rotate it that's going to want to open up. So you remember those little paper things that kids used to make? You could open it this way and close it and then open it this way, right? If you have any rhombus built into your part, when you forge weld it this way, they'll seal, but it'll pop open one side. And then you turn it, and when you forge weld it this way, boom, it pops open the other joint. So you're always opening a joint. It's prying itself apart. So if there's any rhombus in there, the only way to get it straightened out is to really put good heavy weld down into X right here to hold it in place so that the metal can deform and collect. Or if it's really bad rhombus, like ugly rhombus, you got to do some tricky stuff like this. So this goes on the power hammer, and if it's ugly rhombus, I weld it on the diamond. So I can take a bar, fabric pattern material, put it in here, and forge weld it this way. So it rams everything back into place without distorting the pattern too badly. They call them squaring dies. Right, this is just my redneck version of squaring dies. Makes it nice.
Where is that?
This, oh yeah.
Or is it going to big hammer?
No, that one goes in here. Clamps to the side of it, and you just. I just use a clamp to clamp it to the bottom die.
Like you fill it for cheating.
Right. I do everything with a power hammer. I like even the taper or the forging the blade. Like look at this.
It'll warm up the more you hit it.
Making it chicken fried.
Can you see that?
Nice.
Right. So I mean, on a knife, I can use that to forge the thumb. So it forges the bevels on the blade. So I can. No, I'm swinging hammers for suckers and chumps.
No, I know.
Right. No, so I come in here.
Wrestled you, bud.
I know, right? I'm gonna break my rib, break my hand off, and throw it in the desert. Yeah. So with this, I can literally pull the blade through there and forge the taper on the blade under the power hammer. You know, and these are just little pieces of leaf spring
about that today.
with a mild steel back welded onto it, and then this is just 1-inch mild steel. Make a hoop out of it. And it's just a very simple, about 17 little, you know, if you need more taper, you can drive it in a little deeper. Or I have another one that's at like a steeper taper, but this is pretty good for most hunting knives.
What if you want to put a fuller in? Well, it's more you get to see the tool, right? That's the question.
How do we get robots to do this?
So if I need a fuller on a blade, it goes right there. And then I can come in this direction and forge my fuller in. I have two different sizes too. I also have this one that fits in the tool. So I can run a fuller across the bottom or stretch. I'm lazy. I'm remarkably lazy. Let me be the first to admit this. So, here's my rivet head. And my hot cutter. What's another one? Like ladder pattern? Have y'all ever made ladder pattern?
Not yet.
Yeah.
Where you have to
Tried.
grind notches? I just do this. I drop this in the power hammer. These two forged notches in the bottom, and this one is offset in the center. So I just put my material in here, hit it, advance one tooth, hit it, advance one tooth, hit it, and it bends the zigzag in the bar.
And then you just grind the tops off. Grind your
And you
high
just grind the high spots off. Boom, you got your pattern.
Have you ever done Texas winds?
Don't even know what it is.
It's just a wavy pattern, wavy ladder.
Check this out. when I used to travel and do demonstrations and I didn't know what hammer I was going to be using, I made this little tool to make ladder pattern. So it has the offset, the bars are offset, it's built in, but these blocks act like kiss blocks under the power hammer, so it can only drive it shut so much. And see, it leaves a gap between the bars, and that gap is the thickness that I want my finished bar to be. So I forge it to about 3/8 of an inch, then I can drop that bottom half on the whatever power hammer or press or whatever tool they give me, put your work in there, put the top half on, boom, boom, lift up, pull back, index off of the front notch again, drop it on there, wham, wham, just drive it down until it bottoms out.
And it's even every time.
It's even every time. And then since I built this thing like prison style, I was all going fast, I didn't have anything, or I just grabbed the bean pot out of the scrap barrel to make a handle for it. So it's just, again, probably not the best handle, but it works great. Gets out of the way, you can line your parts up. Kiss blocks are built in so you can drive it all the way down flat. Another tool that's always really handy, they're called a hack. Right? So sometimes you got to cut Damascus. If you're making layers, you want to cut the Damascus and bend it back onto itself. The more traditional style, have you ever seen that? Like the way the Japanese do it, they'll draw it out and then cut it and then flip it and draw it out and cut it and flip it. I work by myself, and if I want to get rid of a piece of metal or if I want to cut it off, I came up with this little tool, which is it's just a power hammer hack. So the bit here is built out of H13 tool steel, and it's just welded into a mild steel block. So I've got 1-inch kiss blocks, 1 inch by 1/2 inch back. I did a simple rope twist on it, but if you put this thing down on a surface, it's just not a 1/16 of an inch underneath it. Let me tell you why. Because when you're cutting and folding, I don't want 2 separate pieces. I just want a notch that'll let me fold it. So I can put this on the power hammer die. I can drive this rascal all the way down, boom, 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 until it bottoms out, and it leaves a tag on there that acts like a hinge so I can fold the material back over on itself. And then there's no way that I'm going to drive that hardened metal into my power hammer dies. Because I've got mild steel, this thing drives down and stops, and leaves your little tag, your little hinge piece underneath it. So this thing is just super handy.
And whatever you're...
Little Giant, God knows what they make them out of. The big hammer, what's that? 4140, which is probably what the Chambersburg is also. The Chambersburg probably 41 or 4340, depending on the day. Those dies on that Chambersburg were forged. So somebody forged those on a much bigger hammer. And then stuffed them in there. And it has cold shuts down the side of the die, which makes me nervous, but I want to run it until it blows up.
It's made it this far.
Right? I mean, it's like 80 years, they got to do something, right?
You don't think the Navy was easy on that thing?
Well, I think, yeah.
Or that one, the Navy was.
My last will and testament says to run the small hammers through the bigger hammers and the bigger hammers through the big hammer, right? And then
kind of a turducken.
Right, and then exactly turducken, right? We'll have big blue parts and shit all around the Chambersburg, and then then you're supposed to just start the Chambersburg up and go full throttle. Just put a brick on the throttle and walk away.
Yep.
Let it run until it eats itself. That's gonna be a hell of a yard sale when I go.
So, not a blacksmith. What is a cold shut? I know casting a cold shut is when you have 2 channels that don't quite.
So in blacksmithing, a cold shut is where, as you're forging, the power hammer die might notch into a piece of metal. Yep. If there's not a good gentle radius on there that gives you a contour that can then be driven in, if it's standing up too much, the next blow might
push it back
and close. So basically, it's a fold in the metal that is not welded.
I see.
And if it's open to the surface, it'll look like a crack.
A lot of guys would do that on the point.
Right, tips and edges and stuff almost always have like little cuts and stuff like that.
Gotcha.
Right.
I understand.
Yeah.
Because a lot of people don't know it.
Yeah.
Exactly.
Yeah, that's what I
did it once and
You can kind of see it
cold
there.
shut, and I'm like, how does that apply to?
Well, it's because in forging, if the material is hot, like really hot enough, there's a good chance that a cold shut would actually, or a lap, would actually weld itself up.
Right.
Could actually, but in today's steel production, it's really not uncommon to come across what they call lamellar defects, where there's these defects where you have a chunk of slag that was inside of the melt, and as it's being rolled out, that chunk of slag just gets smeared through the entire piece, and It's just two pieces of metal laying on top of each other with a layer of slag or trash between them at that point. So, you know, as you're, especially in welding, as you go to make a connection above or below that, you know, the weld, the shrinkage stresses of the weld can actually peel those lamellar defects open. And then, you know, what was supposed to be 2 inch thick steel behaves like 1 inch or whatever the depth of the defect is. And then you're in trouble. And it's super common to see that with lower quality import steels, you know, and that's the world we live in.
Yeah, I was gonna say, I've seen like little traces of it, like down pieces of like smaller steel like that. Yeah.
Let me pick all this junk up and go out with the next. Just until you know you're.
Oh, punch it, yeah.
This last one, we can go.
Yeah.
Stay right there.
Our church used to have a few that made
Something I would be selling one like,
Well,
for work for you. There's like one of the friggin' big, like,
there's one in
like 2,000
Well, because here, you look, you can see where the pattern starts spreading here?
Yeah, where it deforms.
You know, I don't mind if I have a little bit of deformation because it'll just cut off on the next one.
Yeah,
Right.
so you keep losing it.
And then up here,
See it?
see it right here?
Right there.
That's where it collected. So on this end, I'm going to lose a little bit more. I'm going to be up here.
So do you ever take all those big thick end chunks and go? Oh,
I'll throw that.
I can't leave that
No,
alone.
I'll throw that in muriatic acid.
See how
Let it soak and get the mill scale out of it, and then I'll just forge weld it together and collect it up, and that'll forge into my least favorite word, low. Because I'm not going to bother spending a lot of time restacking that and doing stuff to it.
Funky anyway. It's not gonna.
But if you stop and think, that's half of that other billet.
I know.
I'm going to throw it away.
It's $20 for the steel.
Right. So this, I can weld it together and draw it out. Well, here, look. I've got some right here.
Make a low layer and then make a little simple thing.
Well, yeah, like, look, here's a couple of little cow tongues that are forged out of that.
Yeah.
And after I forge it out, I find my distortion.
Yeah.
So, like, here, look, there's the end of that one. See it right there and right there?
Yep.
Right,
No, it's
right.
actually-
So this, I would say that everything from here forward is good. And then,
Minus,
whatever distortion up here. But, like, dude, if you're forging to shape, that's a lot, man. I can make a bird and trout, I can make a chef's knife, or if I can hit my mark. So like on this one, that's still a decent, that's a decent chunk. Yeah, it's not enough for a knife, but it still has pattern in it.
Because of the size of knife I can do.
But watch. Why can't I take another narrow billet and then just use that as a put that as a component layer in another billet? So now I'd have layers going this direction, but then a layer of W going this way, you know? So I can incorporate that. Yeah, I mean, look, that's why I have these little shorter pieces, is so that I can use 1 inch wide. And a lot of the time, my target width on this stuff is 1 inch wide, because that's. Now this is 1 1/4. Yeah. But if 1 inch wide, I can incorporate that in another billet, and it just becomes a little component part. I don't know if you all have noticed this, but like over here, there's little treasures everywhere. This is all in progress Damascus. So I mean, this is like, this one needs to be welded and re-squared. This one is here's a component. Like, look, there's 2 different patterns in there, and that'll get welded together. Here's a big chunk that just needs, like, it might be drawn out and used inside of another pattern somewhere. Because
Or just tile it and go from there.
it's too big and too ugly to be used by itself for you.
He gets my age, he won't get this far ahead of himself.
Well, when his eyes go that bad, he goes, "Oh, that matters."
Well, and you know, some of these are just welded but not drawn out. You know, because I used them as a demo.
Okay, so the stainless one is that what? Is there
Semi,
something?
17.4 pH on the outside with 1095 in the core. So that's stainless and precipitation hardening steel semi.
And then what do you? Is there special? I mean, you just run the same forge you are.
I do fucking it sticks. I do AEBL and 154 CM all the time.
No problem.
Problems at first when I started, until I figured out how to not have problems. You know, but there's a feather pattern in the works. Here's a big old component billet. Like, look, that one's waiting to be 4-barred. You know, here's a big chunk like off the end. So there's another end chunk that we were talking about. I don't throw them away. I draw those out. And after a lot of refinement, a little dot.
Come on.
70, 78, 79, 80.
No, I don't. I just want to.
Yeah, I think probably like 81.
Interesting. 1/8 inch on each side with the nickel welding rod. Okay. So it's a layer of silver with
Yeah, I went
1095 on each side with the nickel welding rod. And that's forge welded the nickel welding rod.
Yeah, I haven't.
And when that edges out, it keeps that.
It's kind of cool. I was just up there on
Shining bright shine.
We're going to,
You've got here to dark light and then just straight through.
fire.
You're just taking, you're not going to flex out the rod. You know, like, look, this is a component bar, but it's the same width as my. So it's never lost. I mean, it's the same width as my stacks. Yeah. So on this one, I'll have layers going this way, and I'll make my stack above it. And all of a sudden, now I've got this beautiful pattern that has layers moving in opposite directions, or different directions inside of that. Yeah.
It was still,
You know, so it's still only when they get really fine here.
nobody outside
Hearing permanent staff, what they're cut off has become a record of fire, which is what's sitting on the table. How often do you
shut them down for a while.
recreate the same pattern, or you always just give next one, next one? Why not? Yeah, the last one was fucking old. That was it's already been there.
Yeah, managed to save it.
But if you had someone that shut up and said, "We can heat up a chunk of metal. You can run this thing if you want." Oh shit! I just don't worry, Rob. Everybody won't be watching. What you guys can't hear is that I'm screaming in my head every time when I'm running it. I'm just Yeah, for pattern welding, it's just brute force and just keeping it sharp. It has nothing like architectural work, and when I do a chef's knife like an integral, that's where you start really kind of enjoying because that's where you're working, fullering in to isolate a bolster and really working the heel of the corner of the die to pull the heel of the blade back out, and tapering and forging and keeping your mass where it needs to be. And one thing that's nice about this is that when you start getting really wide and thin, this thing has enough hit to keep moving the metal. Because a lot of power hammers just run out of steam when it gets wide and thin. They won't move the steel. They just kind of slap it. And this thing goes wham, and it gets it where you want it. But I need to adjust the oiler for summertime, obviously. I found that man eBay. They had it this list. I got it for $100. And it's the exact model off of this hammer. So that's why I was like, I don't even need it, but I'm gonna buy it. Yeah, but I gotta straighten it out because I am like it's not gonna hurt anything. During the winter, it takes so long for the oil to heat up.
That steel was in that oil.
Yeah, you crank up the oil a little bit, see that smoke drips a little slower. But now, I mean, it's 70 degrees. I've been out here forging, and it's 22 degrees. Have y'all seen induction forges?
Just demo, or just online.
What are we doing here? Why are we even here? Let's use this little nub. Go 3 tons and barely grab them.
I don't understand half of what it's
Oh no, you're good. I just you're just kind of looking at stuff and moving around. So much stuff to check in.
Dark enough?
Let's set up for half a shop of this. Hey, I count myself for you.
Yeah, this is a brute force machine. Seconds. Let's look at the display. Oh, that's count seconds.
It's on the second cycle.
3 minutes to be cranking the blower on the
That's the time. I'm not sure what give you.
That's like amps or
The top numbers are...
Bottom number is amps. This is a 15 kilowatt forge. So I mean, I let off the pedal, but we're at almost a minute right now.
Yeah.
So 50 something seconds, and we're to good forging heat. Getting scaling heat now.
It'll get too hot.
Oh yeah, but there's no atmosphere. So on this one, if you want to forge weld, you've got to use, and you got to use flux a little bit.
this is right now 240.
Yeah.
Understanding how do you press the button, why it works.
Yep. Gotta do something with it. Let me put it over here.
20 hours of spinning.
Yeah, so for stuff like that miner's candle holder that I was just doing,
You gotta have it.
Still all day long. I'll give you what you want. Use that.
That's just stupid. Yeah, because it heats up so fast that heat doesn't travel quick enough to get to the yeah, and localizes.
so for bumping up, twisting, anything like that, those things, they're just great.
Let's say you can use that instead of like a torch for when you're trying to do like, reverse twist and things like that, right?
Yeah, and you can get a really looking make
Like a C shape or a buckle shape where you can actually slip that face on the outside.
There's my Corona bottle coil. Here's my blaze coil. Here's a pancake coil. You're working sheet metal and stuff. Which part? Right there. So I mean, the coils are just made. It's just a little nub of tubing, and then the coil is just 1/4-inch copper. I use refrigeration tubing because it's thicker than water distribution line.
Yeah, it's more uniform.
Right, you just bend it up, solder it in.
And it's just water you're like, right?
I'm using a mixture. It's ethylene. It's glycol, right? Because it does get out cold as hell out here. So I use a little glycol in the chiller. So it's just a TIG chiller.
Because whenever you send one of those, right? Cheap.
I bought that one. It was I think $25 because the pump was broken, and I called the pump company and bought a high flow rebuild kit for less than $100. So I think I have
Showing off the induction forge.
Oh, cool. I bought the US Solid. I've had this for 10 years now. Really, 8 years now. Yeah, I've had it for a long time. Well, I bought it. Well, I don't know. I bought it for $900 delivered. Right. Yeah. I think now they're still $1,100 or $1,200. But I'll tell you, if you're doing small stuff like tongs, if you're doing small little twists, a lot of the tiny stuff, the newest coil I'm going to make is going to it's going to be this coil, but I'm going to take one leg and make a smaller coil up top. So I have a small diameter coil and the larger coil. So that way you can, as the section reduces, it'll heat better. But when it's 105 degrees outside, and the absolute last thing I want to do is be pumping 200,000 BTU of heat into the damn shop, this stupid thing, I can roll it over, pull up a chair, sit by the power hammer, and just with hand tools, drop stuff in, do little detail work or finish work as fast as you can feed it through the machine. And this thing has cycle time, so you can set your heating time, retaining time, and cooling time. In a fit of America, hell yeah. I set it to D-Day. Right? Because I was like, it's still. And then a little later, I set it to Pearl Harbor, like all these different. So I always set that to something like, hey, that America did something, It's been a good Chinese piece of shit. They make a wand that you can use. So it has like rubber beads and a wand. But you can set, like I said, your heat time, retain time, and cooling time. And then you turn it from manual to auto. So So I mean, if you want, you can set up fire breaks and have it where you put a piece in there, step on the pedal, go over and work one piece, come back, swap it out, step on the pedal. While that thing is sitting there chirping and warming something up, you're over here forging. You know? And I use it for annealing brass because you can adjust your current. So I can set it. I'll take junk brass, something that's cracked or messed up, and I have a little wood deck that fits underneath it. The foil is flat. I have it set where you can drop a piece of brass in there, hit the pedal, and it, with the heat time and dwell time and amperage, it just heats it up perfect. And I push the little lever and it drops into a bucket, and I drop another one on top, so I can just anneal brass as fast as you can drop it in there. And it's been a pretty handy tool. If I fuck up a knife, I should have said that. Cut, edit. So if I screw up a knife handle, when somebody brings me an ugly knife and they want the handle replaced, right? The epoxy that you use to hold the handle on, I mean, dude, it can be a nightmare to break that stuff off. So I mean, it's like, you know, trying to beat it with a hammer, trying to grind it or sand it. You put it in here and just run it back and forth for a quarter of a second. Since the metal is heating, the epoxy just pops off. Just melts the epoxy, and the epoxy's gone. You get back in there, dress it back out again, and you got to be careful not to wreck the temper of a blade, obviously. But it's a great tool for stuff like that. Burning paint off of stuff, you know, just or cleaning outer coat off of stuff because it's heating underneath it, you know. But it smokes like hell, man. I mean, it's just God, it's ugly. How are we doing on time? What time is it? Did I make it worth everybody's time yet?
4:35.
Still do something else. Still time. We can also.
Were you going to talk about how you get the pattern out? I know you demoed it over there when everyone was around, but you haven't talked to anyone else about it.
Yeah, let's pull up a chair and I'll do that real quick.
I was trying to figure out what the order of that pattern was. You said it's the history.
It's the same start.
Oh, same start but different end results.
Right. So all of these are the same start, different result, different end results.
So they all started from those.
This was the initial. Then there's two pieces of this between layers in here. Then this welded 6 times back and forth. 1, 2, 3, 4, 5, 6 became this pattern.
Okay.
This re-squared on the diamond became this pattern. See the 3 dark tick marks? See 1, 2, 3 dark tick marks? So this is the same.
How those two tipped in and tipped in. Okay.
This 4-barred became that. And then this by itself, 4-barred, became this. So this is 1, 2, 3, 4 pieces of this. So same start, but because it was so big, I was able to just cut chunks off and make different patterns.
Okay. So you said gather around for your seat so you can lecture? You guys missed the induction forge. He even has this thing that allows him to heat up flat stock or sheet as an induction.
What are you going to do with the video?
Hopefully get it up on YouTube. Only problem is I need to get it processed like I have Rob Gunther's one, and I process it, and I never click the go to YouTube. I'm hoping to get them all on YouTube. I'll try and get the links to the group, but if you want, my name's Tom Noblit Gonzalez, and like if you look up Tom Noblit, Noblitt, I think there's like 2 of us on YouTube. It'll have me in like medieval gear because I usually do SCA stuff, but I'll try and get the videos posted there. He says it can get to welding temp. The problem is you're there with all that oxygen, so you got to use a lot of flux in order to protect it. Otherwise, it'll because you have all that air flowing into it. So he said that you would have to flux it in order to.
Yeah. I guess you flux with that though. You're not fluxing propane force. At least you got to keep the hell out of your fire break. You know, just drop the flux on the floor, right? You know, sweep it up and go again.
Well, I just wonder about it coating the coils or whatever, how that would work out. Doesn't care?
The coils aren't the source of the heat. The coils are just carrying the electricity.
But the flux won't stick over anything?
Oh, sure, but who cares?
It's just copper tubing, right?
Right.
He also said it's good for cleaning off epoxy from knives because it heats up the metal underneath, so then the epoxy just goes right off of it.
So far, so good.
Pep, you're not helping my bank account.
I'm not here to help anybody's bank account. I am here to be the bad guy, so that when your significant other is like, "Do you really need that?" You could be like, "Point at Pep," right? I was over there. It's free everything. It's like, yeah.
You have to want me to make money this year. I have to get one of these.
Right? My wife's like yours. She says, buy it if you want it.
So, the pieces of metal that I handed around earlier, you'll notice that the pattern appeared on the end of the piece of metal, right? And that's problematic because the pattern appearing on the end of the piece of metal means that, like, if I forge a knife out of it, the pattern's going to be on the point of the knife. That's not where we need it. So somehow we need to translate the pattern from the end of the piece of metal to the sides of the piece of metal. And there's several ways that this can be done. You know, the two most traditional ways are a method called the accordion method, and the other one is a method called the Filicietti flip, or they called it actually the Filicietti method, or then an American guy brought it over here and got credit for it. It was called the ferry flip. But both of those are very effective at translating the pattern from the end of the bar to the edge of the bar. Now,
You need me to move?
no, not at all, man.
Just smack him. He's a minion. If he's not hit, he's not happy.
I see the guys that
No, I don't think that's how that works.
So check it out. In the Filicietti method, what you do is you forge the bar down to half its height of the width, right? So in this method here, I've got a bar that's about 1 1/4 inches. So I'm going to forge it down to 3/4 of an inch. So that would be, this bar would be 1 1/4 inches wide, 3/4 inch thick, right? And in doing that, now we end up with a big long bar of material. Let me get the two pieces that this was cut off of so it kind of frames it better. There it is.
He knows where everything is in this shop. It's scary.
Well, because things go back where they're supposed to be, man. Come on.
Heresy. Heresy.
Right, and this is my own shop. Right, so here you can see I've got this bar that has been forged down to 3/4 inch thick by 1 1/4 inch wide. Right, and the act of doing that is called pre-stressing. There's a reason that we forge it down, because we're going to get into a little bit of math, and for this I apologize. But what we do is cut slices of this bar at about realistically 1.5 times the thickness of what we want the finished thickness of our blade stock to be. So here I'm aiming for 1/4 inch blade stock, so I'm going to cut it about 3/8 of an inch thick. So these slices are 3/8 of an inch, and they've got to be at an angle for greater than 30 degrees. 30 degrees is your minimum. This is 45 degrees, okay? Now, the reason that we do this is because, remember, the pattern is appearing on the end of the bar, correct? We're trying to translate said pattern from the end of the bar to the side of the bar. In order to do that, what we're going to do is that this bar now, the pattern is on the end. So let me get a piece of scrap metal. There we go. Pattern is on the end of the bar. Tracking? 45-degree cuts. Look what happens when I do this. You see that? So now all of a sudden, the pattern that was on the end of the bar is translated to the top of the bar, and I have a scarf between the two pieces now, where I have a good weld joint built in there. You see that? So slice, 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 flip them over, pattern's on the side of the bar. So that's called the originator of this was Steve Filicietti, who was, I believe, an Australian bladesmith. But Tom Ferry went and worked with him for a little while, and they picked up the method and brought it back here, and he got credit for it as what would they call it now, the ferry flip. But realistically, the bladesmithing community was pretty generous about that and really didn't throw too much of a fit. And this has just become a common method of, now it's called tile welding, right? Where we take these tiles, we flip them over, and you can clearly see that the pattern is now on the end of the bar. You can see it even in the saw cut, or the remnant of the saw cut. You can see the pattern. Now this is great because what this does is it provides exact copies of the pattern repeating down the side of the bar, right? But now what you're going to notice is because of the fact that we squished it, you know how have you noticed that it's shorter this direction? So the pattern is still stressed, right? But in the act of forge welding it and drawing it out, we're going to forge weld it and it's going to stretch. And we continue to forge it. You watch the pattern when you're forge welding. You'll see it in the scale. And you just work it until those blocks are no longer compressed. And you work it until they're square again. And that way your pattern goes from a point of pre-compression where we're narrow and wide, right? We do our saw cut, flip it, and now we have these tiles that are overlapping each other, but they are still wider than they are the narrow edge. So our pattern is still compressed. It's compressed. It needs to be stretched this direction to bring it back to normal. Now, the thing to consider here, the reason we have to compress it so much, remember I said we have to go half of its thickness, is because anytime, here's the math part, anytime we cut at 45-degree angle, a 45-degree triangle is whatever X and Y are, well, let's use this actual things, A, B, and C. Pythagorean theorem, man. A squared plus B squared equals C squared, right? Or if you use trigonometry, A or B, they're both the same in a 45-degree triangle. If they are the same, C is going to be 1.41 times either A or B. Now, we're not really cutting a 45-degree triangle. We are kind of actually, but we're kind of abusing the privilege a little bit. But by pre-compressing it, we have to pre-compress it a lot because when we cut diagonally through it, that's already going to grow the pattern a little bit, right? And so we need to really crush it down so that when we cut diagonally, it's still compressed a little bit so we have room to forge weld it and draw it out. So if we don't pre-crush it, you're going to end up with a pattern that's just like really elongated. It gets really stretched out, right? So you really got to crush this rascal down, cut your slices, and that leaves you, you know, like you can see here, my width is 1 1/4 inches. My height is maybe a little under an inch, 7/8 of an inch. So that extra thickness, remember I was saying you want to cut your slices about 1.5 times the thickness of what you want your finished stock to be. That gives you that enough room to forge that out and draw this material out until you get back to square, where your pattern is no longer distorted, right? But that's a, you know, it is what it is. It works well, and you get a very, very uniform representation of said pattern. But a lot of saw cuts, a lot of fit up, and then when you go to do this weld, realistically, what I do when I make this weld is I'll take a piece of sheet metal or a piece of scrap, and I make a sandwich out of it. Let me just get a piece of just for the sake of showing it. So I'll put all these pieces of metal. I'll put a piece of metal underneath it, and I'll TIG weld all the seams, and then I'll typically tack weld it to a plate, like a training wheel.
All the way around, or just on the sides?
I don't get too crazy. Oh no, when I TIG weld them, I weld all the way around.
Okay, so 360.
Right, because otherwise, if there's any inconsistency in thickness or anything like that, you're going to end up popping the joint or having them slide past each other. So it's just this method is pretty labor intensive. Every method is labor intensive.
Yeah.
But this one in particular, I'm not a big fan of it.
Okay.
And let me tell you why. I'm going to get there. So, Feliciati method, ferry flip, cut, flip, stack up, weld it. Accordion method starts the same roughly. Here we're going to take a piece of metal. We're going to drive it down to where its thickness is about 2/3 of its width. Okay? So follow along. Whatever I want my finished thickness of the blade to be, I'm going to draw a line down the side at that thickness. Whatever I want my finished thickness of the blade to be, I'm going to draw a line down the other side. Okay? So I'm drawing 2 reference lines. One that's the finished thickness from the top, one that would be the finished thickness from the bottom. So if I'm aiming for a 1/4 inch, this bottom line is going to be a 1/4 inch up. If I'm aiming for 1/4 inch, this top line is going to be 1/4 inch down, right? Then what I do, let me erase all of this just to get this out of the way. I'm going to cut in to the bottom line. I'm going to cut up to the top. And I'm going to cut up to the top line. Cut down. I'm going to cut down. I'm going to cut up. I'm going to cut down. I'm going to cut down. I'm going to cut down. And then I'm going to cut up.
Is that about a 1/4 inch, or your finished thickness
About
in
1/4
width between each one?
So look, now this material's gone. 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 That material's gone. Have you ever cut paper dolls when you were a kid? Did you ever see somebody make paper dolls where they folded up a piece of paper, they cut one? That paper doll looked like a paper doll from here, right? When you're looking straight down at it on the piece of paper, you cut the outline of it. But when you open it now, once you unfold that paper doll, that pattern repeats. So here, these all unfold, and what was the end of the bar, now the pattern is presented on each one of these facets. And the neat thing about that particular method, it's super wasteful, which is awesome. You get a bunch of earrings.
Have any of these not been wasteful?
Don't crush my dreams, man.
But you're the dreamer of the dreams.
Well, you got to be a killjoy.
Can you hand me your keys before you annoy the guy with the big heavy tools?
I have sharp things. The neat thing, so with the Filicietti method or the fairy flip, you get these very cookie cutter, boom, 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 replication of a pattern, which is cool, right? But with this method, you get a much more organic flow of the pattern, and it's because we're not cutting the pieces, we're not separating them. Anytime you separate a piece from a billet, there's an opportunity for misalignment of your pattern. You just saw me fidget for 45 minutes because I didn't like where mill scale was on a freaking candlestick, right? If lines don't match up, it looks very rudimentary to me, and it makes me not happy. I've literally thrown patterns in the trash because lines don't match up.
Don't throw them in the trash, save the press.
Right. So with this, what happens is the areas of extension and compression, the pattern is never truly interrupted. It's always connected. So in the valley, when you open it, there's an area of extension between the two faces. In the peaks, where it's getting hammered in, there's an area of compression. So you end up with a pattern that repeats down the side of a bar that shows areas of compression and areas of extension. Compression, extension, compression, extension, compression, extension. But it repeats rhythmically down the bar, and all of the lines and facets connect. Let me dust this off really quickly. And because of that, you can get some really interesting dynamics. Here's another one that was stretched in much the same way. Cool. But here, because of that, the way that it's done, all of the lines connect. Everything flows into itself and back out of itself. So you end up with a really kind of a neat, I don't know, it's just everything lines up if you did your job well, you know, so you can get some pretty interesting techniques there. Now the third method, and this is my preferred method, because of the fact that I'm a forge to finish and most of the stuff I'm doing is like integral knives at this point, what I'll do is I take a bar like this. Almost everything I forge it to the largest available square on my last weld. So that what I mean by that is, you saw how big my billet starts? I'm going to drive that thing down until its height and its width are about the same, and then I'm going to collect it and sharpen everything up, and I'm going to try to make it as square as I can and keep the pattern as large as I can. Because I can make a big pattern smaller, but I can't make a small pattern bigger. Right? So then once I get this to this location, I have more math to do, not just this 1.41 thing, right? And here what I'm doing is, you all know that steel is, at this point, for a blacksmith, steel is clay, right? That we don't have to deal with physical forms. We don't have to deal with, I need 1 by 1. No, I need a volume of material. So for me, 3.5 cubic inches of metal will forge, like these knives are 3.5 cubic inches of material. Okay? If you look at this, you can clearly, with this one, the nickel in it, you can see it narrows here, narrows there, narrows here. So this is 1, 2, 3, 4 pieces of the same metal, right? So what I did, one of them got forged into the handle. So there's 1, 2, 3, and then the fourth actually got driven in and turned into the tang in the handle. So what I do is, I look at this, and I figure out how many slices of this I would need to get 3.5 cubic inches. And have somewhere around, when I'm done, I'd like to have it be about 5/8 thick so that I have enough material for my bolster, my integral bolster. So I do the math and I figure out how many is 3.5 cubic inches, how many tiles I would have to cut. So instead of this extremely wasteful process in the accordion unfold, that accordion unfold I had illustrated up there leaves you a bazillion little tiles. like this. These are all, I got the bag a little too close to the fire up here. These are all little widgets that are the cutouts from the accordion unfold. Now these things are gold, I'm telling you right now. Let me tell you why. This little widget was cut out of right here, right? It has every bit of pattern that went that way is represented in this widget. So I'll take this widget, I'll heat it up, put it in there, peak up on the power hammer, and then whomp the crap out of it. And it smashes it out into a flat little coin that has all of that pattern in there. Then I throw them on the surface grinder and grind them out, and I either make necklaces out of them, golf markers, banjo, like whatever, anything. Buttons for, I've had people that had driving coats that wanted buttons made for their coat. Make them out of these things. So these things turn into money. It's kind of fun. But it's still a wasteful process. You're still chopping a bunch of your material out and just kind of throwing it in a pile. With that method I was telling you though, that 3.5 inch method, I can grind the sides of the billet, right? I can cut my slices. Usually it's about 3 slices of that material. And then I just take those slices. So I've got my slice of material, right? All I do is stack 3 of those slices. You tracking? You following along?
You rotate it. You rotate it. And
These would have your pattern here on the sides. Okay? But now here's the trick too. I want to get a little more mileage out of my pattern welded steel sometimes. So one way to do that is I will wrap this in 1095. So around the perimeter of the entire little stack that I just cut, I'm going to put 1095 around it like a frame. And then down at the bottom here, I normally add about 3 or 4 slices of 1095. And that's because I'm going to forge the tang out of that part. So I want it to be tool steel, but it doesn't need to be patterned steel. You see what I mean?
That's it. Nobody's going to see it.
But it's still a great high quality tool steel. It's going to be forge welded in. It's going to be representative of the rest of the blade. It's going to have the same metallurgical properties. It's going to be everything that you want to see. But by adding that little 1095 stack on one side, or by putting that perimeter on it, as I hand this blade around, it's kind of difficult to see, but you'll notice there's a border around this entire blade of just jet black, and then that pattern appears in a band down the center, and it's forge welded and forged to shape. So I mean, it closes around the entire thing. Then this is driven in, and that pattern actually, the pattern welded material ends here, and all of this is actually that 1095 I stacked at the bottom. And this is forged to shape. This is straight off the hammer. It's been heat treated. I ground it enough to where I could see the pattern so I could make sure it wasn't goofy, and then I heat treated it, and now it's waiting to be ground into a finished blade. But the cool thing about this method is that in some of our pattern welding, you might want to use a livelier metal like nickel, or if you're using trash mascus, which is like, you know, I found a couple bandsaw blades in the backyard.
That's me.
Right. If you don't know the quality of your material, this method here puts high quality tool steel on every one of those edges. Right? So I mean, this method is essentially, have you ever heard the term sanmai?
Yeah.
3-layer? Everybody thinks of sanmai as this direction, right? Metal, tool steel, metal. Why not think about it this way? It's the same thing. Metal, Damascus, metal. So I'm taking that sanmai concept and just turning it on the thin edge. Yes, sir.
I was going to say, I've seen Al Pindre do chevrons of roots and pattern welding, which was
There's an idea here.
impressive in an insane way.
So when you do that, where do you? Because you always put a pole on the end to hold it when you get it into the forge.
No, when I'm doing this, I'm doing it with tongs.
You're doing it with
Because
tongs.
this is a very complicated weld. In this weld, you're having to work every side. So I'm having to put it in there vertical and pat it from the top. I'm having to turn it sideways and pat it from the sides. I'm having to make sure that those welds are collected and then keep working it from the front and back, because with it as tall as the stack is, if you let that thing bow at all, when you go to flatten it, it's going to pop the welds on the bottom open. So you have to be very, very deliberate. I mean, that Chambersburg does a pretty good job. I don't have a billet prepped to this stage, or I would love to show you. I mean, this isn't something like, when I get to this stage, I'm like hyper focused on finishing that one task. I don't usually just pause and throw it in the corner. which most of the stuff that I've been forging on today is like the chucked in the corner paused billets that are work on them when you get a chance kind of things. But this is where those go. And let me go get one finish knife real quick.
Pause you.
So this was made using this technique. So here you can see there's one replication of the pattern that's split, and I always split the last replication because I want the pattern to flow into the bolster, right? Because I need people to see that that wasn't cut or ground, that was forged in there, right? Because the pattern doesn't lie. If I cut that out, the pattern's going to be a honk with the chunk lobbed out of it, and that sucks. But what you'll notice is the pattern actually ends right here. And this whole chunk right here was that the pattern comes down onto the bolster, but that was the end of it. The rest of this knife is all the 1095 that was in the bottom here. And then this is, if you follow the lines, one replication is between the dots. So you have 1, 2, 3, and the fourth and final. So this was 4 slices off the billet, stacked on top of each other in this method, forge welded, and then once it's forge welded together, I don't want to set this thing down again. Let's just drive this into something over here. I'm kidding. I'm not going to hand this around because otherwise you end up like this, right? Okay, so I'm going to put it, if you haven't seen these, I have them on the table in the other room in there under the light, so feel free to check them out and look at them. Yeah, I forged this billet on Steve Swarzer's power hammer in Clearwater, Florida. I went to do a demonstration, and Mr. Swarzer was nice enough to let me stay at his place, and we sat and told stories and forged on his big old hammer. He has a 200 just like mine, like identical. Yeah, pretty cool cat. But that's why the only reason I haven't sold this one because I'm kind of emotionally attached to it. Once you start with this big old bar,
Is that blocking your view, Eli? Okay.
when you get it welded, you're going to end up with a cube, right? After it's welded up, and typically, actually, I should have drawn it correctly. Once it's welded, typically you're going to end up with a bar that's shorter than what you started with, that has a border of black around the edges. And then a heavy band of black at the bottom. And then we'll have however many replications of your pattern repeating in it. Right? You knock that thing over sideways. Erase this. Is everybody clear on these concepts? Can I erase this? Okay. So we take that bar and set it over sideways. So we have the heavy black down the side, a little bit of black on the front, and then our pattern's running through it. And what I'll do, I put it on the power hammer and using a square tool, or a butcher, excuse me, little triangular butcher, I'll come in here and notch in on the back. And by doing that, it tips this metal out a little bit and gives me kind of a weird horn off of the back of this thing. This thing, I very carefully go in here and try to drive that down so that by the time I'm done, I end up with a weird little tapered chunk and then a block of metal that looks like this. And that's what sets that pattern down into that, what's going to be the tang of the knife. Right? From here, I can come in and draw out this material and make it into the tang. So then I end up with the tang of the blade, what's going to be the bolster of the blade, and then a block of material up front. I take that material and I forge the end and draw it out, but you got to hit it hard because you want this material to flow out. You know that if you hit something softly, the core of the bar acts like an anvil, and the surface will move, but the core will not. Right? Have you ever pulled out fish lips on something when you're forging by accident? Where if I take a piece of metal and I hit it gently, if I'm not moving the core of the bar, I'm going to end up with an end condition that looks like this, where the surface has moved faster than the core. This is how you know if your power hammer is sized appropriately for what you're doing. If you can hit the metal hard enough that you end up with a bulge on the end instead of a dome, instead of fish lips, then you're moving the core of the material at equal or greater speed than the outside of the material. So for this one, you really, if you want to get it right, you got to be able to move the center of the material as fast as the outside. And in doing that, what ends up happening is now you end up with a little tang, the bolster chunk, and then we draw it out to a point, right? This is still thick. This is still 5/8 thick. But now we've established the rough profile of our blade. We come in with a double fuller and cut in right here with a double fuller on the power hammer. And what that, are you familiar with what a double fuller on a power hammer looks like? Probably not. Okay, check it, yo. Super complicated tool. This is the evolution of grilling tongs. And when you use this, you have to click them twice or something's bad is going to happen. Just like tongs. Right? It's the rule of grilling, isn't it?
Oh, yeah.
You know, flip the chicken before you go out there. You're like, I don't know if the grill's ready. Yeah, we're good. Flip the chicken. With this, check it out. See that? I put it under the power hammer, smashed the crap out of it. And that isolates that bolster. So, I mean, this is exactly what I've just illustrated here. I've pulled the tang out, I've driven this material down, but I come in with this double fuller, I pinch in here, flip it over, do it from the other side, flip it over, do it from the other side. When you're working under a power hammer, you always want to flip your pieces like a pancake at IHOP because you have a couple of inconsistencies in your tooling. It's always there. And if you work in one direction and one direction only, you have natural tendency to be low on one side or to grab weird or different. So if you strike, flip, work, flip, come at it every different direction you can find, you tend to kind of cancel out a lot of the inconsistency. Now, there's a neat tool, super rare, called hydraulic forging presses. They make this stuff a hell of a lot easier on certain parts. Forging presses suck for drawing a blade out because the second that you touch thin metal with a forging press die, it's in intimate contact with the die. It sucks all the heat out of the metal. It's very hard to draw metal out, thin metal, on a forging press. But if you're punching holes or fullering in notches or stuff, it's absolutely the way to go. With a power hammer, you got to be a little cautious. But this is literally directly off the hammer. You can see that fits the contour of that bolster absolutely perfectly. And by doing that, what I do is, coming in right here, I isolate this blob of metal on the front now is isolated from the bolster and from the tang, right? So then, at this point, it's just simple math. I'm going to forge the heck out of this heavy stuff with a power hammer until it stretches out and becomes, so here's the bolster, here's the tang, until that metal moves where I want it. And that little blob of metal will quite literally, and these are about this is honestly about proportionally accurate, but that little blob of metal will become a full-size kitchen knife. But in doing that, unlike the accordion method where you have inherent waste and a lot of layout time and a lot of shenanigans and boogery and instead of that, when you're doing those blocks captured inside of that frame that holds everything in place, the welding is still a little more technical, but man, it makes it a heck of a lot easier to get that pattern to coalesce and to get the mass where you need it to draw everything out and make the final knife that you're looking for. Cool. Yes,
so
sir.
there were three different methods,
Yeah.
right? Okay.
Yeah.
Right on.
And there's even more than that. Like when you get into it, there's a lot of old boys that'll cut tiles and then they'll do sand mai.
Yeah.
So like we talked about sand mai, they'll take a piece of tool steel and they'll actually lay very thin slices, 1/8 inch thick slices of metal down the side of it, and then put that in the forge and weld it together. Like Steve Swarzer loves that technique, and he'll do essentially sand mai with a pattern on the side and the edge being whatever metal of choice is. But again, it's entirely dictated by the machinery that you have. Everything that we do is dictated by the machinery that we have, because we're working so far beyond what you can do by hand that if you don't have some kind of power forging equipment, it's going to be hard. If you do have some power forging equipment, it's going to be hard.
So for like if you had some power forging stuff, like if you had a hydraulic one that moved slow, or like you were talking about, you could do it with the larger stuff, but once you get down to drawing the blade out, you need something that's kind of gonna come up and just hit it.
I'd rather have a 25-pound little giant than a 20-ton hydraulic forging press.
Right.
When it comes
For
when,
that part of
when
it.
it comes out to forging a knife, let's just take a piece of metal. I'll take a piece of let's just forge a knife real quick out of just a whatever scrap chunk of whatever I've got. You pocket band-aid? Why, thank you, sir. I'm bleeding like a stuck pig. That happened like hours ago.
Oh, did he?
Hi, Pep, how are you? I made a little mouth on my finger. All right. So you know what I'm going to do? I'm going to go ahead and fire the forge back up again. I'm going to find a suitable piece of metal, and I'm just going to go from square bar to forge knife with that hammer and that 25 in the corner, and maybe the 100. And I'm just gonna,
You got the ensemble going, like
right.
you said.
I'm
They're
gonna
all your
definitely-
drums.
I'm going to try to do most of my work here so you can see how I do it with the fuller and whatnot. But I will most likely draw the point down on the 25 because it has drawing dies on it, so it won't hammer little notches into it as it brings it down. It'll actually allow me to bring it to a point, a good contour. So let's take a half a second break. High five amongst yourselves. Let me stop my hemorrhaging and I'll fire it up.
Record,
This is
leave you
I was taking that
alone.
flipper out. We spark test this.
See, I used the cheaper, lower quality camera earlier in the day with those batteries, the 6 different batteries. Now I'm using this one for this demo. I'm doubling up just in case with the second camera. Not that I've had cameras fail on me at the most inopportune moments. No, nay, never. Finals of Crown. Clack. So how many times have you guys felt called out, using scrap maskers? Oh, this is a piece of bandsaw blade I found on the Oh, forging by hand, there's only so much you can do. Oh, twists in this pattern, those random patterns, those are boring. Why would you do those?
Set up a block like this. Hardy cages.
I don't do any pattern around it, so it's all new to me.
Just a little. Well, this is kind of like when you, for Joanne, whenever someone's showing like how to spin fine silk and do something, they're like, oh, you'll get there someday, dream big. This is more like someday we might get to this ability. Now here's the part that sucks, Eli. You've already gotten spoiled at Thomas's shop. Soon you'll graduate and not have that, and you'll have to build your shop from scratch like me.
You can file.
This kind of thing.
The biggest thing I'm going to miss from Thomas's shop is being able to fit the material that I picked up off the ground.
I was going to say, the biggest thing I'm going to miss from Thomas is spending time with Thomas, because that's like, how do I do this? Here's the answer. How do I do this? Here's the answer. How do I do this? Oh, you use this tool. Then you're at home and you're like, how do I do this?
Yeah.
Crickets. Oh, let me figure out something.
Generally, it's how do I do this? Well, this is the hard way. What's the easy way? Well, this is the hard way.
Why are you calling me like that? It's not like I always only think of the hard way to do something. Every now and then I think of a semi-easier way.
Would anybody like a cup of coffee?
Sure.
I've got 2 French presses and a whole tray of coffee in there. While this forge is heating up, let me go grab it. I'll be back out here and I'll have a coffee tray. We'll have a little afternoon caffeine burst. Give me half a second.
I understand.
Okay, I guess while everything's warming up, so we can see how fast it's striking.
Oh yeah, the smaller the faster.
Don't you have one about that size?
Yes. Or you have someone wanting to come look at it. See about buying it.
Is it someone we like? Or someone we need to run off? So quiet.
Straight off the hammer.
They didn't put that little clip in there.
What's that?
This way the hammer works.
You're driving hard.
They're coming for everyone else.
Yeah. Everyone else, the other people that don't trust me. So with the power hammer, if you come in behind the tip, you got that square end. If you come in behind that square end, it's going to push that metal out, right? So I kind of come in, it pushes that metal out, and then I work my way towards the tip, and that metal gets pushed out and worked into that fine point. If I immediately just go for the point and try to knock it down, the ends are going to move forward and close up, and you're going to end up with a shut at the end of the bar. So like right now, that thing is forged to a fine point, and it was forged on a fine point, like on the 1 1/4 inch cross section, but it didn't close up because I started back away from the edge, crushed it, so that made that edge push out, and then I worked towards the edge, and it brought that edge back out again.
What kind of dies were you using on that hammer?
Those are just fullering, or those are just drawing dies. So, I mean, if you didn't have drawing dies, if you're doing this by hand with a hammer, what you're going to want to do is to, you can either work here to where it's going to push the middle of the metal out, or another thing you can do
How fancy is that?
start here, knock this corner in, right? Once that corner's knocked in, flatten it back out again, and then go over the edge of the anvil, and when you're hitting it, it's gonna fold that edge over the edge of the anvil a tiny bit, and you can knock it, kind of hook it on the edge of the anvil and drive it back into itself. Let me get some mild steel, I'll just do one by hand so you can see the technique. Because if you do it that way, it hooks on the edge of the anvil and you drive that sucker in, and then you just come back and they've got the point.
I love how so much of this stuff is operated.
Oh yeah, I love foot pedals.
Especially handy to keep your nose to the grindstone.
You know which side's the edge?
This side, every side.
Trick question. Right. This is going to be the edge. So Tom was nice enough to finish brewing the coffee. There's a bunch of coffee mugs, sugar, half and half, 2 French presses full of dark roast, nice and hot, sitting back there. So if you need coffee or anything like it, it's right there. Help yourself, please. So forging a point, not on a power hammer. You can hang it over the edge a little bit, knock this corner in. See that little beak? That beak hooks on the edge of the anvil, and I'm driving it down. Now I can work all the way around the nose of that thing, but when I come back on the anvil, instead of making a shut, that thing bends up. You see what I'm saying? So instead of ending up with the frog lips, what you're going to see is that little piece, now I come back, I forge it, it turns up, and I got a nice flat surface on the top of that thing. So you don't get that little bite, that little fish lips, whatever you want to call them. Tighten this up a tiny bit. before I just go back to the fire. We got this weird looking beak now.
Yeah.
Right? So here I just have to decide how much metal I need for my handle and go with it. All right, now what I'm going to do next, I'm going to flip this thing around and put it back in the forge. I only need that much metal for my handle. Just guesstimating. Right? This is 1/4 inch thick. My handle's not going to be 1/4 inch thick. I'm going to forge it into a beautiful taper. So I have just a tiny little bit of metal in that handle. And the rest of it's where it needs to be, man. I'm not going to waste Damascus. So the handle's going to taper from 1/4 all the way down to dang near nothing.
Are you going to do hidden tang with it? Is that what you're looking for?
No, I do full tang on everything. Hidden tang is what I do if I run out of metal. So like right now, if I put this in the totally wrong spot, hidden tang! Yeah.
Have you ever looked at doing the handle first? So that you've got something to hold, you know, and you've got a point out there.
No.
If I do the handle first, then I can hold the phone better.
You know, the reason I do it this way is because I can make the biggest knife I can with the metal that I have. If I do the handle first, it's when I'm making a blade of, if I'm making, you know, if I'm using mono steel and not Damascus, because my thing, I don't want to end up with like an 1.25 inch little square of leftover metal. So if I've got a couple inches of this stuff, I'm going to draw it out. I'm going to use what I've got. I'm going to make a big knife out of it, or I'm going to make a small knife out of what I got. So this, I'm just looking at the size that I had. Right now what I'm going to do is I'm going to drive my fuller in here, maybe a little in front of that line. I might come in up here. And then I'm going to come in back here under the tong and drive in it again. And I'm going to have a little lump of metal between the two. Very similar to what we did at the demo, right? So I'm going to have a fuller. My dog's home. And then I'm going to reshape this metal in the middle. And then after that, I'm going to go to the little giant. And once I have those two locations, I'm just going to keep drawing it the taper until I get the proportions correct. Does that make sense? So notch, notch, taper this direction until everything moves to the place where it's big enough for a hand to fit in there. Tracking? The lady in the green is my lovely wife who's put up with enough of my today.
Hey, for coffee?
She's the one that made the pecan chocolate chip cookies and set up the coffee and did all that stuff. So, because I'm an insensitive bastard, I wouldn't have done that. I would have let you all like rest uncaffeinated for the rest of your time here. Okay. So juggling, let me finish the point on that one I was hand forging, just so you can see that technique to completion. So here I'm going to start backing it up onto the end of the anvil. Nice sharp point, no shuts, nothing to trim off. If you do get the little lips, it's no big deal. Put it in the dang vise, trim the end off with a cutoff. Do it at a little bit of an angle so you have less to move back, and you'll be fine. You know, see there, you end up with a good point with no shut on the end of it. Okay. We're going to use a single fuller. I use this one because it's about the same size as my finger. So this is going to forge the finger notch that forms where your hand holds the blade. I really work hard to try to make blades that your hand can't ride up in heavy use. Let me grab a knife to show you what I'm talking about. I like a knife that has a good deep finger groove here. So this is what we're going to do with that fuller. Is we're going to go under that power hammer. We're going to set the knife up like this, and we're going to come in here and drive this in. That's going to give us that notch, and then we're going to come back and drive this in and give us a back notch here. So we're going to isolate the mass, and then I'm probably going to come over and do a little bit of work right here. Can you all see that contour? And I'm going to be hitting it with the round side of the hammer right here to give myself that contour right there. That's what you want. That's what I want. And I'm the one making it, so that's how it works, right? Okay, what do I do with the floor? So basically all I'm using the power hammer and that fuller for is a substitution for the horn. The nice thing about doing it this way is that driving it down into the metal keeps the back of the blade flat. So I don't have the distortion from hammering on the back of the blade and trying to use the horn to support the other side. We're going to get there soon enough. So now I've got a ridge in the middle, but it's got sharp points at the edge that need to be driven back in again. So I'm going to go upside down on the anvil and drive those points in a little bit, but then I'm going to use the horn, the contour of the anvil, to get a good shape in there. So again, I'm going to come in here. got a little bit of the shape in there. But I want to get a kick on the back here a little bit. So we're going to go take one more heat. Actually, I'm going to take it to the power hammer and stretch it out just a tiny bit. I got my proportions a little, I mean, they're already pretty darn close. But I'm going to draw it out just a tiny bit. Questions? I'm just kind of tinkering now, man. I'm just working, and this is mono steel. It's a piece of leaf spring. So quite literally, I was trying to figure out what demonstration to do for y'all. So first I was going to show you how to do forged dividers. Like this. So I thought, hey, that'll be fun. Forged dividers. That's got kind of slow. Demo was a little tedious. A little tinker timey, you know? So then I was like, I'm going to make a flipper knife. And then I thought, man, you know, I don't want to take a drill press or have to punch holes or do anything fun. But this flipper knife I was making out of that piece that we're using now. So that's why I know it's spring steel. I forged it down to this. This would have a hole in it, you know, where it could flip around. Yeah.
So when you're sizing handles, how do you decide, you know, I mean, because
I go like this.
I mean, is it like your hand, or do you like make ones for big hand?
Here's the story. So I forged a bunch of knives, and every time I had a buddy that came over here, and every time he'd pick up one of my knives, he'd look off in the distance, and his shoulders would rock back. He's like 2 tours in Afghanistan. He'd grab that knife, just look off in the distance, get that 1,000-yard gaze, thinking about it. Then he just put it down and just be like, and I was like, it looked like I just got a fart, you know? It's just like you just got something in the wind. I was just like, dude, every time he put it down and just kind of nod his head a little bit, and just not disgust, but pretty darn close, you know? And finally one day I was like, Josh, you know, coughing. I was like, what is it that you're like, come on, man. Like every time. Now this is a knife user. This is somebody that was in Afghanistan and in Middle East. And over there, they didn't respect guns, but they sure as heck respected edged weapons, you know? And he told me, man, when you pick up a knife, it should feel your hand. It should feel like you're squeezing a lump of clay. And you should know exactly where the edge of that knife is at all times, regardless of how it is in your hand. You know, that it should index. And that's what closed me in on this design, was that when you close your hand, you know, if you look at the shape of your hand, there's a void in here. It's thin at the pinky, thin at the ring finger, but there's a big bulge in the middle for you to grab. It's the same when it's upside down, but there's a place, you need a place for your thumb to be when it's upside down. Because you don't grab a knife like this upside down, you typically index off the back of it. So I kind of closed in on this design because it should be like what he said, it should feel like you're grabbing a lump of clay or like you're holding onto a golf ball. And even if you have large hands, that shape indexes quite well in the hand. that knife make it around safely? Nobody's murdered themselves by accident?
Themselves? No.
So I'm going to take one blow to clean up the fuller in the front, and then we're going to start using this tool here. And this tool here has a taper built into it, and it's going to actually forge the bevels into the blade, so that we don't have to do it by hand, because handwork is for suckers and chumps. We covered that already, right? Okay. Don't worry about it getting all freaking willow leafy or wanky or anything like that. We'll straighten that out right now. The majority of the bevel work is almost done right now. So I mean, all we got to do is just get in there and kind of true it back up again, and then do a little bit of light forging and bring it back up. Whatever. Take another heat, we'll start pulling it out longer and forging our taper into the blade, and then keep it collected. This is going to turn into, it'll grow about an inch longer maybe. All right. Sometimes. What's that?
Oh, a little tool you got at another shop. It does in a hardy hole, and it looks like a miniature ankle board.
Oh yeah.
The thick or whichever?
Like this?
That only much smaller.
The front hole on this anvil is actually tapered. So the front hole on this anvil is actually 4 Pexto stakes, which is I've never seen before. Yeah, the rear is 1.5 inch hardy hole, but the front is a Pexto stake hole. And look at this. I mean, Normally I put an old leather glove over the hole and then drive the stake in on top of it to take the wiggle out of it, but it's tapered.
What's the brand of the oven?
Atwood. Very old, very strange. I've never found another one. Yeah, but with the tapered part, the tapered Pexto stake hole in the front, pretty rare bird, you know? And it is handy for shit like stuff like this. Because you know, you can come right in here.
Any of you guys want to do iron in the hot tickets? We're doing $5 per ticket, 2 tickets max. Just because it's a small bid today.
Take it off? Drive back to town? I got it.
Iron in the hat. You have change for 20? I should.
Good seeing you. Travel safe.
You heading out?
We gotta go snake, man.
Why don't you just hand in the 20s?
Alright, yeah. Right on.
Thanks again for making it out.
So that, are you
Always
getting one?
appreciate it.
How late?
Okay, so 2?
I don't know, man. I'm gonna after the forges turn off, the refrigerator opens.
You gotta be here at 7, so you're running till midnight, I'll come back.
Text me if we're still out here. Come on out. So I'm not going to push this thing all the way to totally finished. So I'm just going to run a couple more beats to refine the shape and get the taper in a little bit better. And then I want to show you a tool that, if you for power hammers, that because power hammer dies are flat, right? So if anything is tapered, you're in uncharted waters, right? So there's a little tool.
So just hand it to you, right?
Just called power hammer flatter. So this thing, you put it in there, whatever direction your taper is, and it allows the power hammer to adjust, essentially, to a wedge shape. So with this, I can come in here and clean up those bevels very precisely. Right? Just a simple tool. I mean, and I build all of mine now. I used to make them all crazy and fancy, but now I just use 1/4" rod, welded, because if you hit it wrong, it can bend. Doesn't transfer a lot of shock in the handle, which especially with the flatter. If you have the flatter out of alignment, it'll buck the heck out of you. So with the flatter, this is, you want a handle that will give a little bit. Getting it here, you know, it's hard to get a knife, especially when you're starting off with a 1 1/4 inch. It's hard to get something that's too much wider than